Welcome to the Volumetric Media Interoperability Town Hall 2025. For those of you who weren't here last year, it's a new version of the good and well-tested Town Hall format that we did previous year. So without further ado, about a couple of words from our sponsor before we get started. So this organization is organized by Metaverse Standards Forum, which is an organization that assists traditional standard setting organizations. It's a neutral venue. We do not produce standards ourselves. We rather engage in pre and post standardization activities. Pre-standardization meaning developing requirements, for example, and post-standardization referring to testing and other usage-related topics. It's a fairly large organization, and we're approaching these various topics in a very pragmatic and bottom-up approach. As you can see, the organization is fairly large with 2,600 global members and counting. Here's a couple of examples of the organizations that are present in MSF. And in terms of activities that the organization is engaged in, here's a list of working groups. And I have to provide a disclaimer here that this isn't exactly up to date. I got this from a 2024 presentation. So some of these working groups might have changed, but the broad category of working groups still largely remains the same. So there are groups focused on 3D interoperability, digital twins, engagement and education, ecosystems, technology stacks, legal and use case related verticals. And a little bit of background from our working group, which is Volumetric Media. We were established 2024 with the intention of facilitating discussions across various organizations that are setting standards related to volumetric media. And again, we're not producing standards ourselves. Our group consists of around 100 individuals with very diverse backgrounds. A little bit of a background for the town hall itself is that during the 2024 feedback for the town hall, we identified a theme that people would have benefited from more background or understanding of what volumetric media is about. Instead, we were focusing on showing the competencies and capabilities of what volumetric media can achieve. And for that purpose, we kind of tailored the focus for this particular town hall to take a step back and give a bit more educational presentation this time around on what type of volumetric formats are out there and what sort of use cases could go along with them. And another part of the town hall today is to talk about what sort of shifts and advancements we've seen in the landscape during 2025. And the expectation really here is to have a very honest and a direct discussion on how to enable a healthy volumetric media ecosystem. And on that note, here's the agenda. So we will start with an introduction into volumetric formats from Joey and Ralph, who will be presenting a 3GPP SA4 study on Beyond 2 video, which did quite a good work on inspecting the markets and checking out what sort of volumetric formats are out there and what sort of use cases and capabilities each come along with. So we're going to start with this brief introduction, and then we will be diving into these a bit more specific segments. And starting from implementation of standardized codecs for dynamic point clouds and dynamic meshes. This will be a shared slot between Patrick, Kay, and Guillaume. Then we will continue with moving from dynamic meshes to 4D Gaussian Splats. Here we will hear from EverCoast, from Ben and Sebastian. And from there, we will go over to Christian from Philips, who will give us a presentation on end-to-end system for live volumetric sports. And then we will hand it over to Will Eastcott from PlayCanvas, who will give us an introduction on the beyond the tech demo production workflows for Gaussian splatting. And with that, we have our wrap of the first segment of the town hall. So we'll have a quick break if possible. And after the break, we'll continue with Alex from Looking Glass on holograms in the real world, challenges and opportunities bringing holographic displays to the market. After that, we'll hand it over to Michael Rublow from radiancefields.com who will go over a brief 20-minute summary or overview on volumetric video markets. And after that, we'll be providing a brief update on our own survey results, which we run on an annual basis to see where the volumetric media has evolved over the past year. And then we will get to a great highlight of the town hall, which is the panel discussion on focusing on various different formats and use cases. And here we will hear from our great panelists, Devin, Marius, Alex, Ben, Wilfred, Denny, and trying to summarize everything in 10 minutes at the end will be our own skip to provide you a summary of the meeting. And then by 11 a.m., hopefully we'll have things wrapped up nicely and we can move on with our day. Good. So that's the first 10 minutes. And I think it's about time to hand it over to Jerry and Ralph. So which one of you is going to be sharing?
Yeah, I will share the slides. So let me take over. Yeah, and Jai will start and I will then take over in the middle somewhere and then I give back to Jai.
Okay, so hello everyone. My name is Jai from China Mobile Research Institute. I'm currently a 3GPP delegate and also serve as a reporter for the Beyond 2D study. The topic of our presentation is Introduction to Volumetric Formats based on 3GPP Beyond 2D study. Since the media formats and the codec directly impact the visual quality of volumetric content and transmission efficiency, and also the interoperability across multiple devices and scenarios. So we believe this is an important topic to be addressed. So Ralph and I have prepared this presentation to walk through the overall scope of 3GPP Beyond 2D study, including a general overview, the end-to-end reference model, and also the scenarios we considered and evaluated during the study phase. Yes. So from this figure, we can observe that from traditional 2D image and the videos to today's high definition videos, the advances in the network as well as the media technology have significantly improved the quality and the user experience of the visual application. So what is the next? And can we further enhance the user experience in existing services, such as streaming, communication, and messaging, by integrating the visual signals that go beyond the traditional 2D video? So we believe that with 6G network and the advances in the media codec, the video service are expected to evolve to meet users' growing demand for the immersive and interactive experience. From the visual perspective, it will upgrade from traditional 2D video to Beyond 2D and the volumetric video formats. From the audio perspective, it will upgrade from the model to the multi-channel and immersive soundscape. And from the interacting perspective, it will upgrade from traditional keyboards to the multisensory interface. However, unlike the mature ecosystem of the traditional 2D video, there is a variety of volumetric video formats and the processing workflows are available and emerging, which creates the interoperability challenge and hinders the widespread adoptions of volumetric video service. For example, in this table, we summarized some major volumetric representation formats and the candidate codecs. So in order to determine what's the appropriate formats for different services, it is essential to evaluate their feasibility and performance. So to address this issue, 3GPP have initiated a study on Beyond 2D video in release 19. And the scope of this study is to first document the Beyond 2D video formats and the codec, include the stereoscopic video, multi-view plus depth, dense point cloud, dynamic mesh, nerf, and 3D ghost splatting. And we then established a set of the end-to-end reference workflow for Beyond 2D video service. It includes the UE to UE stereoscopic video live streaming, streaming of professionally produced volumetric video with a single access containing people, and the streaming of multi-view plus depth produced content. And for each scenarios, we defined a specific evaluation framework, include the test conditions, KPIs, test sequence, and reference signals. And we then evaluate the performance of potential representation formats and compression technology, considering the requirements such as the network boundaries and the latency. So this study began at the March 2024 and ended in June of this year. So the entire TR report is currently public available for people to review. So this is the generative reference model we developed. The purpose is to harmonize and support different beyond 2D surveys and scenarios. So in this diagram, the interoperability point 1 is natural contact, which includes the UE-based cameras and sensors, and also the professional captured multi-camera arrays. So there is, and the pipeline in the, I think is in the third. So this is the pipeline for the AI and the computer-generated contact. The interoperability point 2 and 3 define the data processing stage, which includes the conversions of the captured media data into the standardized beyond 2D format. And the interoperability 4 specifies the format of the compressed beyond 2D video streams, and interoperability point 5 represents the decoding and the recovering process, where the streams are reconstructed to the original format. And the interoperability 6 is the rendering and the display format, which is usually implementation specific. So the evaluation work we conducted during this study focus on the point 3 and the point 5 of the reference model. Yes, so I think Ralph will give people the presentation on the scenarios.
Okay, I take now over. Hope that you can hear me. Yes, I'm happy to present you the 3 scenarios that have been deeper studied in the Beyond 2D study. So we focused first on scenarios that are really, I would say, short to midterm. And one is UE to UE stereoscopic video live streaming. So UE, it's user equipment. So we see on the left side, we have here a phone with 2 cameras that can record a stereoscopic content. This is then encoded, transmitted over the network, and it can then be viewed on a number of viewing devices, such as a head-mounted device, another mobile phone, a tablet, or some other pairs of glasses. Today, typically content is professionally generated and not user-generated. So this would be the new thing here. But what we also see is not so many phones have 2 cameras or cameras for capturing stereo. So many have just a single camera for capturing the content. And there's then also the way to send this to the network and to convert it to stereoscopic content by an AI-based solution, which has been studied in Beyond 2D. And then once that you have out of the AI-based solution, you have the stereoscopic video, you can follow the same path as before. So this has been studied. Then we look into the formats that are used. On the left-hand side, we have the source format properties. So typically for mobile phone, you can use full HD, so 1080p, which is a good format. But there can also be larger devices such as tablets, so higher resolutions can be interesting. The other video parameters are quite standard. So 16:9, 4:0 chroma subsampling, and here we see frame rates and bit depth. And for codecs, 2 codecs have been studied here. On the one hand, it's simulcast HEVC, that means left and right eye, each time with HEVC. And then also multi-view HEVC has been tested. And here you see the detailed parameters that have been looked into. And then also metrics and tests is an important part of the report, as Jai was already saying, concerning objective metrics that we have seen, for example, that some content is generated with AI, so one camera and an AI-based solution, and there can be some artifacts that can appear, for example, edge sharpening, mismatch, cardboarding effects, crosstalk, and so on. So here some better metrics need to be studied, and here, for example, this human vision 3D matrix has been studied that looks into the quality of the individual views, so left and right, and also at the fused views, so what really your brain would make out of it, and also at the quality of the depth map. All this has been put together, with some weighting factors and combined together in a single score. So this is an interesting matrix for capturing that. But the tests that have been done in the count study have been done with the typical PSNR methods. So PSNR-Y has been used here. So test sequences have been collected. On the one hand, that came from dual camera generated content that we know. And also, sequences that come from a single camera and which have then enhanced with a second view with the AI-based solution. So both kinds of contents are in. Codecs that have been tested are a simulcast HEVC and also multi-view HEVC, and the matrix is PSNR-Y, and you can see that there are gains concerning multi-view HEVC over the simulcast HEVC. So this is visible. But the study had a time limit, so not everything was finished. But I think for the moment, it has been said that it's worthwhile to do some further investigations, in fact, on stereoscopic video in the context that I explained, and also that new parameters such as camera parameters, depth, alpha, and also improved chroma subsampling formats should be studied. So there will be more study on that topic. So this was the first scenario. So the second scenario is more volumetric. So this is called streaming of professionally produced volumetric video with a single asset containing people. So we hear professionally that we hear single asset. So all content is encoded in one asset, and it contains people, because people, it's something difficult to capture and also to produce. And then concerning scenarios, we see that a number of volumetric production companies that make prototyping of use cases. And training is a very interesting case, and notably sports, for example, to learn some sports exercises that you can watch it from all sides. You can have a contemporary witness, for example, that you capture a person that is maybe relatively old and has an important story to tell, and you want really to capture that person in a volumetric manner, or favorite singer in your living room. That is also an interesting case. So there are many of them. We see that a lot of studios have been set up around the world, and also studio equipment. You can buy it. It's possible to build up studios based on equipment that you buy, that you don't need to develop all by yourself. So we are at the stage that all this is ready. So the dominant representation formats that we investigate in the study are dense dynamic point cloud and also dynamic mesh. So often we see that the production companies produce both formats, or the one or the other. And we also see that some solutions are completely end-to-end. That means companies, they produce the content, and they have also then an app or web-based solution that the content can be viewed on a consumer device or in a web browser. And also, MPEG has finalized codecs for dense dynamic point cloud. So this is called the VPCC, video-based point cloud compression, and also for dynamic mesh, VDMC. This is video-based dynamic mesh compression. So that means also codecs are available and published by ISO. That means all this is available. Here, this video here shows quickly what it is, a volumetric video. So here we see how this is captured. My colleague is moving this a little bit. Now these people are doing some exercise that you see here when you're swiping over the tablet, and you can zoom, you can change the viewing angle from where you want to see. You could also replay it. For example, if you say, this one I missed how this has been done, and I replay it. So this is much more convincing for doing exercises or learning exercise than just with a typical 2D video. We see this is running here on the tablet, that it's running in real time, and this is using dense dynamic point cloud here. But also dense dynamic or dynamic mesh can be used here. For example, here We have from China Mobile, a prototype set up that is very lightweight. On the left side here, you see a capturing system that uses just 4 consumer Connect cameras and it's able to capture with 29.96 frames per second dynamic mesh content with 50K triangles, and texture resolutions from 1 to 8K data. So this is also important to see that with simpler setup you can produce content that. So I think this will be in future also a pretty important case for social media people to capture at home and make this available. Notably for sports training, this looks to be very convincing. So here we see quickly the architecture, how this is delivered. So on the left side here we have the professional production in this rig system. You see all the cameras. Come later back on that. This can be a point cloud or mesh, as I said before. And then it goes here to an encoding system. So we use here in this setup point cloud that in this diagram here, but it could also be meshed. So this is done with VPCC from MPEG and then sent to HMD, tablet, smartphone, or whatever. Here we have also the case that with a simpler setup, and this is the very extreme simple case. You have just one single camera view and you can build out of that a volumetric video so such solutions are also existing or of course content could be completely AI generated. So these are the sources and like this it could be delivered. Concerning the format that we studied in Beyond 2D. So concerning dense dynamic point cloud, we wanted to have a good quality for humans. So we have seen, okay, we need up to 2 million points per frame. And for dynamic mesh around 30K polygons with around 4K texture. This gives good results that you can also go relatively close. And we have also seen that such setups or such configurations run on mobile devices that are on the market today. So this is tested, we hear later, I think, from that. We made also some tests. Okay, if you go to a higher solution, around 9 million points per frame for a person, the quality comes close to the production system. The 2 million we think is a good compromise. Because facial expressions and also when you see close, for example, you see really the structure of the tissue, all this becomes visible, that you could really go closer. And also, okay, if you don't go too close, in fact, also around 600 points per frame, could be used, but then you should not go too close. So these are indications we tested. At the moment we think that the 2 million is a good one. We also investigated the impact on renderer for point cloud, which is very important. So on the left side here, we see the guy is with 600 points per frame. And here we use a very simple renderer. We have just that a voxel is replaced by a cube of a configurable fixed size. That of course, if you make the size too big, you fill the holes, but the face will look blocky. And if you make it too small, then of course you get holes that you need to find a compromise. So here we see that holes are appearing, also scratches are appearing here. So this does not look that nice for the eye, but it's useful if you do compression tests, for example, that you want to see from the original to the compressed, uncompressed content. Okay, what is the impact on compression? Then such rendering is okay. But for visual viewing, it is not so nice. And here we have the same number of points that are on the right side here, but we use another rendering mechanism. We call it splat blending, and that means the splat is opaque in the middle. And when it goes, you go more far away from the center, it becomes transparent.
1 minute.
And makes this, and like this, we have overlaps of the splats, and it looks much nicer. I continue. Then concerning performance tests that we have and the report objective tests and also subjective tests. And the objective tests looked into 2 metrics. One is for geometry distortion and one is for color distortion. And for geometry, we look at the point-to-point error between the original and the decoded one. and also the point-to-plane error when you put a plane into the first one and you look, okay, what is the distance then to that plane, and P's and R's can be calculated. And for color, MSE is used that for YUV, and then you get the objective metrics for on the compression.
Sorry, Ralph. I think we're running out of time.
Yeah, I have 15 minutes for that one.
Oh, it's already past.
Yeah, but normally okay, then I stop on that.
Yes, sorry.
Then let's go to the summary. I hand back then to Jai.
Yes, thank you. So I think during the studies, we identified for stereoscopic video, the extension of the representation format and the compression options was to be studied for in the future work. And also currently there is no support in 3GPP for representation format and codec for scenario 2, like Ralph have introduced. Basically, it's for the dynamic mesh and also the dense point cloud. And there is also no support in 3GPP specification for multi-view plus depth content. So the conclusion we have is that the report concludes that certain beyond 2D video formats are maturing and become market relevant, driven by the advances in capture, productions, compression, and display technologies. However, the broader market adoptions is awaiting, and before we have formal 3GPP specifications. And also, there's a complementary studies of the extension for stereoscopic video, dynamic mesh, and 3D Gaussian Splatting is recommended. And another conclusion we have is study the efficient network solutions and the bandwidth of optimizations to enable real-time beyond 2D video delivery across a wide view range and include potential multiple users or multiple access without compromise the perceptual immersions is also recommended during the studies. So this is, I think this is all for our presentations. Thank you.
All right, thank you very much. And unfortunately, we don't have time for taking any questions in at this point, so we need to badly move to the next segment. But thank you, Jai and Ralph, for your excellent presentation. It was extremely informative. And with that, then Patrick Fontaine from InterDigital, would you go first for the next segment on implementation of standardized codecs for dynamic point clouds and dynamic meshes?
Yes, thank you. I'm happy to present the V3C Immersive platform. It's an implementation of a standardized codec for dynamic point clouds and could be extended with dynamic meshes. This platform intent was to enable deployment of immersive experiences. We work with partners to have access to volumetric capture and editing. So, for example, XD Production gives us dynamic meshes that can be converted in dynamic point clouds, and then standardized reference model and from MPEG are used for compression, and also we follow the V3C carrier specification for the streaming. And the focus of the presentation today will be on the rendering on any devices. So mostly Android devices like smartphone, tablets, and also HMD like the MetaQuest 3. So really quickly, as most of you probably know, the V3C standards can take as an input multiple formats such as point cloud, multi-view plus depth, and dynamic mesh. So the encoders has a first step of 3D processing to project or convert the volumetric video into multiple 2D videos, such as texture, geometry, occupancy, as well along with metadata. All these information are encapsulated into V3C bit streams. And on the receiver side, it's the reverse process where the 2D video component are decoded with hardware, traditional 2D video decoder. So in the platform we are using currently HEVC, and a 3D reconstruction to have the full volumetric video available on the end devices and for interaction with the end user. So the V3C Immersive platform follow these steps. What is provided is a V3C dash packager that takes as an input an encoded V3C bitstream, so VPCC or MIV, and produces the V3C dash segments. And these can be transmitted over the networks to the decoder platform that is split into two components. The native decoder plugin that will implement the decoding part with the demixer of the bitstream, using the hardware video decoder for the video component, and there are synthesizers for each format to reconstruct the scene. And the second component is a host application running with Unity for interaction with the end users and to provide, to request and provide the correct view. So this platform has been recently contributed to the 5G Mag reference tools. It's with a contribution mostly from InterDigital and Philips. And here is a representation of the mapping of the repository that are provided in a kind of high-level architecture. So from the right to the left, you have the V3 stamps here, which is the first repository with test content and some tools and script to use MPEG reference software for encoding. We provide also the V3C packager that could be deployed, for example, on an origin server. And then through the delivery network or through GDPP network, this content can be delivered to an end device, end user device, running the native decoder, which is the V2 repository, and V3C application. So you can find this project on 5G Mag GitHub. So the Unity project enables the decoding and the real-time rendering of the video. It uses a decoder plugin library for reconstructing and synthesizing the volumetric video, and the test content and dash packager and in the third one. So
all right, great, Patrice. Any last remarks?
Okay, so I will just show this last slide, which is an example of the test content that are provided. So here you see an example of a point cloud running in augmented reality on a tablet. Here it's MIV content with parallax, and we also have some synthetic content to show.
Amazing, thanks.
Thank you.
Very good, very cool stuff. Then Kay from KDDI, would you kindly go next?
Yes, I would like to start my presentation. So my name is Kei Kawamura from KDDI Corporation, and I'm honored to have been invited to speak and for the opportunity to introduce our activity at KDDI Research. I'm excited to share with you the latest progress in advancing the dynamic point cloud and dynamic mesh transmission in XR application. Okay, so in this presentation, we focus on the center part, the transmission. So we don't touch the acquisition and the presentation. We focus on the center part only. So in this presentation, we provide several demonstrations. And at first, in January 2023, we conducted a proof of concept of the real-time point cloud transmission using the VPCC, video-based point cloud compression. And we developed the real-time VPCC encoder, and which is compliant with the VPCC, and we successfully streamed compressed point cloud data to the smartphone. And and we also have the So in our demonstration, so we realize the end-to-end real-time transmission from capturing the performance in the volumetric studio to the rendering the life size program on remote stage. And you can see some demonstration video on YouTube, but I skipped at this moment to shorten the time. And after that, we move on to the dynamic mesh transmission using the VDMC codec. So actually, in the February 2025, we demonstrate the real-time mesh generation and the real-time encoding compliant with the VDMC, video-based dynamic mesh coding, and which is and the transmission to the smartphone via 5G. So this is enabling the free viewpoint viewing on smartphone of the dance show. And after that, we also have the similar but a little bit different demonstration. So in October 2025, it's the last month, we enhance our demonstration by developing the smartphone browser, which is also compliant with the VDMC. So it means you don't need any application, but you just see the video streaming by using the browser, even though it is a smartphone. And okay, so finally, we also show the proof of concept of the extra content viewing. In the past two demonstrations, it focused on the real-time transmission, but this content is how to show the demonstration. And you can see the YouTube video. Firstly, we capture the dynamic mesh in the volumetric studio, and we encode the such dynamic mesh in VDMC, but we also add some computer graphics effect, and which is very important to enhance the user experience. And this video can be seen on the Apple Vision Pro. So we also developed the real-time decoder on the Apple Vision Pro. Okay, so you also, unfortunately, the only Japanese announcement and narration is available, but you can imagine how the experience can be achieved. Okay, so let's go to the final slide. Okay, so we briefly introduce the three kinds of the demonstration. First, the point cloud. Second one is the dynamic mesh. Both are real time, but the last one is the extra content viewing event. And from this demonstration and our development, we find the 3 points. The first one is the latency. So real-time encoding and decoding is already achievable, but the codec delay of the several tenths of a second remains a challenge. So one-way real-time transmission is okay, but dual way is a little bit difficult. And the second point is the content. So enhancing the volumetric video with CG effect is significantly improves the user experience. And finally, so we see some use cases, and unfortunately, all current capture is performed in the volumetric studio, but the capturing the live spot and the music events in stadium or concert hall show strong potential. So this is the presentation from the KDDI. Thank you for the opportunity. Thank you.
Thank you, Kei. That was amazing. Thoroughly enjoyed the videos that you shared. Would have been great to see those already before, but this is amazing. All right, good.
Thank you.
Let's hand it over to Gilliam from Tampere University next.
Yes. Okay. So I will present our point cloud encoder that implement the VPCC codec. So our work is open source, and you can find it on GitHub, and on our website you can find many other tools for volumetric and 2D encoding. So let's first dive into what VPCC is. So basically VPCC, we take an input point cloud and we project each point to a plane. And from those attribution, we can generate patches. So patches can be then placed onto an image, different image, the attribute image, geometry image, and the occupancy. Once it's basically done, we can apply that for all the frames of the video, and those 3 videos are then compressed using HEVC. So in this case, we are using Quasar, our HEVC encoders, that is also open source. And we can achieve like almost real-time compression. So here you can see the quality we get. So on the left, we have the uncompressed data. Then the second one is compressed using TMC2, so reference VPCC encoder. And then we have the results with our encoder with the 2 different presets. One is slow, which is targeting offline encoding, and the fast is the one that maximize speed over quality. Here we have the results for different voxel size, so different range of points. And if you can see in the upper left corner, we are able to achieve like 50 FPS encoding with around a bit less than 200,000 points. All of that on a consumer grade machine, so we can expect good performance overall. And here we have the video, like the different quality across the different rate of the common test condition from MPEG, and you can see the speed of the encoding and the compression ratio that we can achieve with our encoder. On top of that, we are also working on capture. So we are trying to provide a data set to the community to be able to evaluate compression aspects. So we have a point cloud encoders, mesh point cloud data set, and mesh data set also. And we also have an implementation of the RFC, RTP RFC to transmit V3C data. So all of that is available on our GitHub and our website. So that's basically it.
All right, thanks you, Guillaume. That was swift. And I have to admit, that's probably one of the best explanation slides for VPCC-based compressions that I've seen in a long time. Really, really good stuff. Do we have any questions? I think we have time for one question for any of the presenters, Patrick, Kay, or Guillaume. Do we have anyone on the line? All right. In that case, in the absence of any questions, yeah, so let's move on with the agenda. And with this, we can maybe save 1 minute, unless I spend it here trying to introduce the next segment. So we'll move over to moving from dynamic meshes to 4D Gaussian Splats, and give it to Ben and Sebastian from evercoast.
Cool. Well, thank you for having me, Laurie, and everybody. And as Laurie noted, I'm, well, he didn't, but I'm Ben Nunez. I'm the co-founder and CEO of evercoast. I am joined by our head of 4D reconstruction, Sebastian Burke. We are here to talk about moving from dynamic Gaussian splat or dynamic meshes to 4D Gaussian splats. And by that, I mean sort of evercoast's evolution of our various pipelines over the years, and what we've seen as the good and bad of these reconstruction approaches and representations. Before I dive in, I just want to give a bit of an overview on evercoast. I'm just going to take a minute on this, not going to make it a big plug for the company, but I think we're one of very few teams in the world who spent more than a decade working with dynamic volumetric data. So I think we bring some good experience and perspective. We've built a platform that encompasses really three main parts. We offer software that, so capture focused. We offer software that enables you to spatially calibrate and temporally synchronize multimodal sensors. So really being able to capture the data to begin with. We have a rendering platform with various models and pipelines that allow you to take that raw spatially calibrated, temporally synchronized data and turn it into 4D spatial video. And now particularly with our 4D Gaussian Splatting pipeline. And then we let you take that spatial data and spatial video and integrate it into your tool of choice, whether that's using the native PLY or OBJ sequences, or we offer encoded and compressed formats that ultimately just make it easy to go use the data. All of this software runs completely in the web browser, so we've made it pretty accessible. We've done this for some of the world's, some of the biggest clientele in the world, and from delivering very high resolution, broadcast quality output down to more cost-effective solutions and a lot in between. So that's EverCoast, and really what we're here to talk about is the evolution of our pipelines and what we've seen over the years, but more specifically our support for Gaussian splatting and how that compares to what we've seen with meshes. And to that end, I'm going to hand this over to Seb, who's going to walk you through all that.
Thanks, Ben. I'm Sebastian. I'm head of 4D reconstruction at EverCoast. I'm going to just go over some of the benefits that we've seen from Gaussian splatting and several real-world challenges that we've faced and have solved to varying degrees. I'll also talk a bit about meshes versus splats and how they're different. And our system generates both meshes and splats from input data, and we can also extract meshes from splats, which is kind of another interesting direction. So meshes are actually quite efficient for representing surfaces. They've got triangles and they've got compressed texture maps. Whereas splats are a bit more, I would say, expressive, and they have a shape and a rotation, a scale, and view-dependent color. And meshes define kind of explicit topology with appearance stored in the textures, and then splats are independent primitives that carry their own shape and view-dependent. So let's go on to the next slide. So I think this kind of illustrates one part of splatting that's great is that they have this opacity and shape, and what allows splats to represent both volumes and surfaces and be able to reconstruct things like smoke and fire, which is cool, but also lets us more critically reconstruct complex geometry like hair strands, fingers, thin structures, things that would take you would need a lot of data and resolution to reconstruct a surface for. You could imagine a hair strand. You could create a mesh for a hair strand, but it would be you would need a lot of high resolution cameras to get there. So what we're seeing here in this drawing is kind of how splatting is an analogy for how it works and why it's very cool, is that it gets these subpixel details and crisp edges that mesh topology have trouble, because it's sort of layering on these different semi-transparent splats like paint strokes. And so you don't have to have each paint stroke being perfect. They kind of one can be off and the next one can kind of help, and they generate a clean image, whereas meshes in some senses require one perfect stroke that you have to get right from all angles at the same time. So just the other aspect that's really cool about splats is that they're view dependent. So they've got this view dependent color, and it does cool things like you can represent shiny materials like the specular highlight in a belt buckle or forehead, so that when you move, that highlight moves. In general, volumetric texture and mesh representations, that highlight would be baked into the texture and you wouldn't see it moving as you move. But I think what's even cooler is that you can trade this sort of global geometric accuracy that you get with a mesh for per view correctness with splatting. And this reconstruction here of Zelensky that Ben went out to capture with some lower resolution real sense cameras and sparse array. We had trouble getting the face with a mesh accurate. Not enough views, low resolution. It's difficult to reconstruct that nose when you only have a few pixels of it. But with splatting, the color is changing as you're changing your view. So you can still render a realistic view of this of him with a proper nose and something that actually looks like him, even though the geometry underneath may not be perfect. You also see this for things like texturing. In a texture and mesh, you're going to need a single texture that's going to have to be stitched together, and it's going to have to look right from every view all at the same time. And so it becomes difficult to get those texture seams just right. And this is something you can get around with splatting, where the texture is actually changing essentially as you're changing the view. So I think that's quite powerful and allows you to actually go to lower camera counts and still get convincing results and have more practical camera rigs. And we've seen for a variety of applications that having someone's face look like them is quite important when when you have a distortion of the nose or distortion of other facial features, you right away know, like, hey, that doesn't look like me. So that's something that's been very beneficial for us with splatting. So another great thing about splatting is that it's very nicely differentiable. So that's partly why we can optimize so many different parameters and optimize something that's this expressive. It's got these nice smooth gradients, and so the optimization is well behaved. The other thing that's great about this is you can integrate it with other generative AI models and diffusion models, because you can you've got the gradients and you can back propagate them. On to the next. So Gaussian splatting generally struggles as the views get sparser. This is essentially, you've got less data to work with. The original Gaussian splatting papers, a lot of the scenes had hundreds of viewpoints that they're reconstructing, and for some of our applications, we might have less than 10 viewpoints. So that leads to kind of a different set of things we have to deal with, and we often end up with some under-constrained optimizations that we have to intelligently regularize, or novel view quality degrades quite quickly as you get far from the original training images. And this actually magnifies kind of most of the next challenges that I'll be talking about. So here's one we kind of found early on is Gaussian, the kind of vanilla version of Gaussian splatting can represent solid surfaces, but it kind of does need a fair amount of training data and views to get it right. It kind of naturally ends up more as a volume. And so some of the other facts, like you can see in this picture, is like you can get foreground that's sort of pasted, background that's pasted onto the foreground, which when you render a certain view, you wouldn't really notice. But when you try to convert that into a mesh, into one representation that works for all views, you start seeing these issues. It can also show up as a transparency issue, where from a view close to the training data, it looks great. And then when you move away, you realize that it's been taking background pixels and using them to render the foreground, and you start getting these holes. So this is something we've had to kind of manage with our different implementations and constrain. Another thing we've been working with is that high resolution texture details demand, in certain situations, they can demand an enormous amount of splats. Particularly when you go to 4K, 6K, 8K data, many views, this starts being, for high frequency detail, you need a lot of splats to represent that texture. Whereas with a mesh, you have a nicely compressed image format. Texture compression is quite mature at this point for meshes and images. And you can think of kind of the worst edge case here would be if you've got like a white wall and or a very highly textured wall, not a white wall, but a very highly textured wall. And with a mesh and texture, it's like you've got maybe 2 triangles, 4 vertices, and then a very high resolution texture. With splatting, you're going to end up having splats for each little detail in there, and then you might need to have some of these splats overlapping, and it can get quite big, quite fast. So there's a variety of papers that have come out in the last year or so addressing this, and there's a lot of cool different techniques. I think a lot of the challenge here is making that play nice with all the other aspects of your Gaussian splatting implementation. And so there's the original author of Gaussian splatting recently published an article where he grouped several issues under the umbrella term mathematical intricacies of 3D-GS. And that includes various forms of aliasing, projection, distortion, possible volumetric rendering approximations that may or may not be good enough, appearance and model limitations. And these sort of artifacts you start really seeing as popping or flickering or blending incorrectly when changing views. And you start seeing them more when you move away from where there's no training views. So, where you have sparse number of cameras. And this also is something that comes up and becomes more noticeable when you start trying to do dynamic 3D Gaussians, and can show up as temporal issues. Can also show up when you have different renderers. You might have one render for training that's CUDA based and fast, another render for WebGL, and you can start having artifacts between the two because they're representing the render in slightly different ways. So we'll go on to temporal. So yeah, continuing with kind of temporal coherence issues. When you're close to a training view, you can kind of just reconstruct each frame as if it were its own Gaussian splat. And if you do that well, you end up sort of inheriting the temporal coherence of the original videos, multi-camera videos that you're using, and it can look rather good. But as soon as you start moving away from those training views, you start seeing a lot more of these temporal issues come up. And so there's been a variety of papers that have looked at how do you deal with these temporal artifacts. There's sort of idea of dynamic Gaussians where you're kind of taking the same Gaussians and moving them from one frame to the next. There's 40 Gaussians, different versions of these where you're actually modeling temporal Gaussians that span time. And there's the static dynamic decomposition where you're looking at, well, there's certain things in this temporal scene that are static or near static, and those you can kind of propagate from one frame to the next and not recompute. And I think this becomes pretty important for reducing the cost of dynamic Gaussian splatting and really making it so you can create a lot of content quickly, which is important for certain business models. And I think that's where you don't want to be reconstructing every frame separately. So there's also runtime things to think about here. And another aspect can be that another kind of thing here is initializing Gaussian splats. So you can initialize from just kind of a random set of points, and then it will optimize to the correct shape, hopefully. But this can take a little bit of extra time, and it can also run into local minima, and you can not get the result you want. So we've before Gaussian splatting, we worked on a real-time reconstruction system that we use for visualization during shoots, so people can see what the result is generally going to look like and fix any problems that are there. And so we've leveraged that real-time work that we've done to initialize our Gaussian splatting, which makes it a lot faster to run and a lot more stable and complete results. The last bit is compatibility with CG tools. So one more slide. Yeah.
Yep.
So compatibility with general computer graphic tools is improving, but it's still kind of early days for that. One issue I briefly mentioned is that each platform requires different rendering algorithms for optimal performance. So, when you're doing the training, you're going to have a CUDA renderer. When you're playing this back on the web, you're going to do a WebGL, and there's, you need slightly different algorithms there. And these things have to be managed in step and changed in step. And then you've also got game engines, Unreal Engine, Unity, that they have different needs as well. And so it's kind of managing these different rendering algorithms can be an engineering effort. There's also integration in a different sense where of actually integrating them for temporal and lighting. And that has been a problem for volumetric meshes as well. There hasn't been a whole lot of great integration for that. They're not like a rig character that you can easily edit or relight, but they were compatible with all sorts of tools in the sense that each frame you could just drop in to Maya or Houdini or Unreal, and it was just a regular mesh, and you could do things with that frame. Which was useful for visual effects applications and game applications. Splats require a purpose-built renderer, and that has to be integrated into each tool, even just to see one frame. And then there's still the integration of lighting and physics that we're looking at as well. So each of these problems is fairly there's fairly straightforward ways to solve. What becomes difficult is solving all these problems in a way where they all work together with each other cleanly, and then doing that for all sorts of different camera setups, different types of data, and edge cases. That's really where all the engineering hours and times go, is getting everything to play nice and having it play nice on many different types of data and applications.
Brilliant. Thanks, Sebastian. I think that was incredibly insightful. And I'm glad to hear that the industry still has some work to do to solve all these challenges nicely. There's one question from Devin in the chat related to the red tracksuit dancer. So he noticed that there are some sharply defined edges along the silhouette. Can you extrapolate a little what's going on there? And how does that interact with the flyaways?
The sharp edges of the splat render, or the
I assume so. I didn't notice them. I noticed them in the mesh version of the late.
Yeah, there's that one slide where we show that definitely the texturing in meshing is difficult, and you can get artifacts in that because it's got to look right from all different views, and that's quite difficult. The geometry really has to be dead on for that to work well. And so splatting, you really get around that problem if what you need to do is just render. We do a thing where we can optimize our splatting for mesh generation, where we really optimize it for a surface. But then if the camera count is low, it's not going to render and play back as cleanly. Or we can optimize our splatting for rendering, where it's really just optimized to view. And so the geometry doesn't have to be perfect in that case.
Okay, cool. I hope that answered, Devin, your question to some extent. And if not, do feel free to continue on the chat. But for now, we will need to thank you, Ben and Sebastian, for this excellent presentation and move on with the agenda. So thank you very much. So next up, we have Christian from Philips, giving us an overview on the end-to-end system for live volumetric sports. So Christian, the floor is yours.
Thanks very much. This talk is about an end-to-end system for volumetric live sports. So not only the algorithms and the formats, but starting from the cameras, what type of problems do you encounter and where do you place cameras, how many, how you stream. I will give you an overview of our choices and why we did that. But you might ask, why are we as Philips working on this at all? Well, here's an answer. We are part of, the next slide, wait a moment. We're part of Philips Intellectual Property and Standards. We are responsible for managing the IP for Philips, but we also license out technology. So we do both things outside Philips as well. This first POC that we produced, we did that together with VodafoneZiggo and AWS. Now, our objectives became more clear over the recent years, and I would want to summarize those. The system that, any system we think that should work robustly, it has to work autonomously, because so many cameras, it's not easy to manage. Another aspect is the installation. Sometimes the installation can be permanent, but sometimes it also will be flexible, and then it has to be fast, the installation process. And also robustness, low maintenance are important parameters. Then regarding results, we want to have them in seconds and maybe even sub-seconds rather than minutes. And then two applications we think are interesting. At first, for the first market entry of these systems, is the replay for the broadcaster. We see that already happening in the Olympics. And the other one is the fan engagement, where interactivity matters and you can navigate the scene. Two quite different use cases, but the same technology behind it. So the system architecture at a high level looks like this. At the left of the figure, you see the capture system. Then we have we uplink everything to the cloud, and there we do the processing. So processing tries to understand the scene. The advantage of that is robustness and speed. So object segmentation, depth estimation, atlas generation, that's for transmission and encoding. Then storing it on a CDN. And then on the right block, you see the decoding part. So this is on your device, either in the headset or on your smartphone. And there is an arrow that is called moment selection. That's an interactive system where we select interesting moments. So the consumer can actually select a moment and get that to his phone. So for instance, switching from a live monoscopic stream to a interactive moment. These figures basically shows our development, going from a setup with aluminum stands to a more robust setup with waterproof systems and recording. And then on the right, we have a cloud system where everything goes to an Amazon EC2 instance. And we also use this tablet that you see on the right to control the system. For instance, to control exposure, color settings, etc. And the whole thing, 8 cameras, plus modems, plus edge compute. That's all in this casing for the POC. Now on a soccer field, the layout will be integrated in the LED boarding. So here's a prototype setup that we used for testing. You can see the cabling, you can see the cameras, 16 cameras in this case, on both sides of the goal. Then 4 times the Jetson trigger cables. We're going to remove those, but they're still in this setup. And what is not shown is the connectivity boxes that ingest the feeds via 5G into the cloud. So here you get an impression of what you need to integrate to be able, and this has to work it, and it has to be robust. Here's another set of pictures that illustrate this. On the left, the cameras, then along the LED boarding, going around the corner of the LED boarding to also view the game from the side. On the bottom left, you see the red rectangle that highlights our cameras, and on the right, you can see a camera node. So it's barely invisible, but in the next version of the POC, we're going to integrate further. Currently, this is the effect that we get. So this is matches that were captured during the Open Cup. It's an innovation cup, 3 days, where we tiled our system in a combination with the broadcaster. We can navigate the scene and generate moments. Here you can see quite a limited viewing zone in each case. So the data originates from 8 cameras in both cases, quite sparsely placed. And you can imagine that the next step, going full around, full pitch, is a challenge. But okay, not undoable, we think, but it will be a challenge. In detail, the system architecture can be scheduled using these AWS modules. So on the left, you can see our capture system. Multiple Jetson computers connecting multiple cameras to these Jetson computers and then powered by a power over Ethernet switch connected to a router. That's the left block. And then on the center, we have multiple Kinesis video streams. That is an AWS video store where we can stream the data. We have communication from the cloud back to the Jetson computers. Then in the cloud modules, we have EC2 instances that scale horizontally to be able to do compute fast enough and compute moments in parallel. Then more on the center right, you can see 2 cloud applications. One is the operator application that is intended for the operator, the person who operates the system, modifies the exposure times, etc. And on the top, we have the client devices that connect to the website to run the WebGL renderer on the client device. And that can then be shown on a headset or on a tablet or on a smartphone. We use the MIV standard to transmit data to the client. So it's Atlas-based, and I'll tell a little bit more about that. In terms of algorithms, this is the pipeline, roughly the pipeline that we already use for quite a long time. So on the left, you see all the issues that have to do with calibration. The calibration pipeline has to determine this distortion parameters, principal point, all the intrinsic parameters of the cameras. That's typically done in the lab, although these days you can also determine those automatically, but it's a benefit to do that in the lab. Then the extrinsic calibration, that is typically done automatically, but that has to be robust. So that's non-trivial to do, and tools like CallMap will bring you so far, but more is needed to get a robust system. Then the third block is the scene calibration. That actually ingests prior knowledge that you know of the scene. Sometimes you know what you're looking at. So prior knowledge, prior learned knowledge can be used in that case. Output is then metadata, and the center column here is the whole 3D pipeline, I would say. So undistortion, object segmentation, depth estimation, depth segmentation, let's say taking depth objects into subparts, then extracting patches. So these are these small regions that you can place in an atlas. And the metadata of those patches are then transferred also with the bitstream. Background extraction, sprite extraction, some parts in the background you don't need multiple vantage points or a very advanced model, you can just texture map those. And then atlas generation at the end. So here's an example atlas where you have the sprite and all the foreground patches that depend on separate views. Now the rendering part is the part that takes place in the device. In our case, it's a specific renderer, and I have to say, so most of these standards that are used, they don't dictate the renderer. They don't specify how the rendering must be done. So there's variations possible. We use a variation where we take up an entire patch, an entire depth patch that assumes continuity in the depth profile. Then we order those in the target view and do a blending compositing operation. So it's a bit like a multi-plane image, but then on a patch basis. It gives a fast rendering result on the client device. So here's an example of how this MIV encoder decoder architecture works. To the left top of this figure, you have the pixels. Then this map is in form of a multi-view, goes into MIV encoder, where we have video data, atlas data, and viewing parameters that constitutes the V3C bit stream. Then we decode that. We do a reconstruction in view space. So we reconstruct back where those patches came from the source views, and we can start rendering. And as I said before, rendering can be, let's say, a point cloud type rendering, even a splatting, or you can do meshes or depth and multi-view. So there's multiple variations. The atlas at the bottom is the one that we sent in these examples. So that's texture, depth in the middle, and the transparency on the right, and a background view. Here's an example of a hybrid mode. So a hybrid mode is a situation where you're looking on your smartphone or tablet and you're seeing the 2D view, and you want to freeze that moment in time to do a bullet time around that moment. Here's what you can see what you can do. You can also remove objects. So it's interactive in the client side. So the client side knows about the patches and knows about where they are in space. Here's an indoor example at the left. The camera system that we have, we want to view that as a broader platform so that you can do more than just the creating 3D immersive views. Once you have the system in place, either flexible, installed, or permanently, you might want to do more in the terms of analytics, and that's shown here. So 3D skeletons of meshes can be computed, and there can be a synergy between computing analytics and doing volumetric video. So those are two different functions with totally different requirements in many cases, but there could be overlap in both. And that's what we want to emphasize with these slides. Then finally, a bit more info on this analytics. If you're looking at such an immersive lower vantage point, so let's say from the LED boarding of a sports field, there's lots of occlusion. So there's lots of clutter of objects, players close together, etc. So in that case, you have to disentangle that information, understand the skeletons, for instance. In this case, we were able to use 2D skeleton detection, but then on top of that, do a number of analytics tasks to make sure that we get 3D skeletons that are consistent and also metrically correct. So to conclude, I would like to look ahead in general, but also what we're aiming for. So what we're aiming for this sports scenario is to increase the look around effect. We want to be able to sweep entirely around the scene and create interesting immersive views where the virtual camera flies into the field and is not stopped by limited resolution. We want to cover the entire pitch. An important aspect for commercialization is to further rigorize the system, the hardware kit, and integrating the infrastructure. We're currently testing, and we will also continue doing that during live matches. And we have set up partnerships with broadcast and production companies. A bit further ahead, commercialization, of course, of this system via third-party platform operators. Thank you very much. If you have any questions, let me know.
Thanks, Chris. And considering that we have 4 minutes for questions, I'm sure we will find some. First of all, thanks so much for this interesting presentation. I continue to be amazed by how much you can actually achieve with only 8 cameras. Looking really forward to see what you can do with the 16 surrounding the full pitch. There's one question from Alexander in the chat. Oh, no, sorry. Where did it go? From William, sorry. It's a question about the camera calibration. I presume you mentioned CallMap and how it gets you only so far, but more accuracy is needed. How do you get further than CallMap?
Yeah, so these tools like CallMap and LS Vision and all, let's say, the more low-level underlying libraries that lie below those libraries are based on bundle adjustment combined with an optimizer like Levenberg-Makar. It's the numerical algorithm that lies behind it, and it solves for the 3D structure and the camera poses simultaneously. That problem is ill-posed always. That means it's very difficult to distinguish rotations and translations in general. So you don't know whether you're looking at the rotation of a camera or whether it's translated slightly. That depends on the layout of the 3D points in space. And if you're looking at a scene, a large-scale scene, and there's not so many objects in the foreground, your calibration can go horribly wrong. So typical setups in an inside studio where you have chairs and tables very close by is the ideal case where these tools work. If you don't have points close by, you have to put more constraints on the system. And that makes it difficult. And that's why these tools not only always work, or to put it differently, in our case, they almost never work. Now, to the answer to this question, how do you solve this? One aspect, thing that you can do is you can solve it over time. So you can wait until there's enough points close by. Another thing you can do is to put more constraints in the system. If you know positions beforehand, you can use those. Another solution is to use known objects. And then finally, you can also put more mathematical constraints in the solution space. But yeah, that is, I think, the situation with calibration at the moment.
Brilliant, thanks. Thanks for the insightful answer. I think we have time for more questions. So let's go for Marius, who asks, what are the criteria that you may choose MIV instead of other volumetric formats such as point clouds or meshes?
Yeah, so to be honest, the pipeline that we use, the biggest problem is the analysis. So the calibration, the conversion, and then you end up with a result. And the nice thing about MIV is that it stays close to the source views and it can still describe view-dependent color. There's also a drawback, of course, because it's not, let's say these patches they live still for a part in the projective space. Splats, for instance, or points, or meshes, they already live more in this 3D space. So they're more explicit, but more difficult to achieve. So these formats all have their pros and cons. In that respect, the reason that we stayed to MIV is that as of now, I still don't see any drawback that had to do with the format itself. Because, for instance, if I image the soccer ball and it is lit by one side, this view-dependent lighting is actually quite easily described by MIV. And for instance, Gaussian Splats have these spherical harmonics, but I don't think spherical harmonics is a natural view-dependent way of working. So view dependence in a simple way, so just having source views with different lighting and then blending those using ray angle. That's what we do in our renderer. Basically, we determine the ray angle to a point in 3D between the viewer and the source views, and use that as a blending weighting operation. And that gives quite a nice transition between one, let's say, brighter color and one darker color, and you have to interpolate between the two.
Very well, thanks so much. Okay, so I think we're out of time for questions for this particular presentation, but Chris, there are a couple of questions waiting for you in the chat. So feel free to look at them if you have time and interest. In the meanwhile, we'll need to move on. So thanks again for this very insightful presentation, and we'll move to Will from PlayCanvas.
Thank you very much.
All right, hello everybody. My name's Will Eastcott. I'm the creator of PlayCanvas. And PlayCanvas is an open source web graphics creation platform. And we've been spending the last maybe 2 years working on 3D Gaussian splatting technology, including SuperSplat, which is quite well known these days. But I wanted today to talk about our journey over the last 2 years, where year one was kind of largely about making tech demos, essentially kind of showing the potential of 3D Gaussian splatting. And then year two has been more about enabling industries to use 3D Gaussian splatting in practice. Okay, so if we look at PlayCanvas's very first tech demo, this was back in October 2023. So I guess we started working on this stuff about 6 weeks after the INRIA paper was published. And yeah, the very first thing we did was just load a PLY and get it rendering in the PlayCanvas engine. And this was a very exciting moment, and it was a very first step into this new field. But since then, we integrated Gaussian splatting as a first-class citizen in the open source PlayCanvas engine. And over the last couple of years, we've managed to integrate a lot of additional features like shadow casting, or things like multiple splats occupying the same scene as traditional 3D mesh geometries, so you can mix and match. We support something called global sorting, which is having multiple splats in the same scene and then sorting the individual Gaussians properly. We can also load massive splat scenes and then stream them and utilize LOD to keep a more or less stable budget of Gaussians that are rendered per frame. We also support picking, so you can do very accurate picking of Gaussians, even though you don't have an underlying 3D mesh to make that easy. And we have frameworks that enable you to do things like custom reveal effects if you want to do something a little bit visually aesthetically pleasing. And also we have a custom shader framework that allows you to do things like custom recolorings and wipes and fades and things like that. So the underlying open source engine that we have is extremely powerful when it comes to just rendering all this stuff. But early on in our journey, we did realize that we needed some kind of application where we could wrangle all of this data that was coming out of the Splat training software. So we built the open source SuperSplat editor, which runs in the browser, and yeah, you can find all the code on GitHub. It allows you to sort of crop and recolor and optimize and export your Gaussian splats ready to be used at runtime. But quite early on, one of the major feature requests that we had was there was a lot of demand for people who wanted to share Splat-based content with other people. So we also extended the SuperSplat editor to be a whole publishing platform. So you can now just trivially publish your Splat content to the web. And now we've got tens of thousands of splats that you can browse on the SuperSplat website. And there's some really, really awesome content there. So I do encourage folks to head over there and explore some of what people have uploaded. But I think when we went live with this service earlier this year, there were, I guess I had some expectations that people were going to upload like scans of rooms and human beings and maybe like chairs and pieces of furniture and stuff like that. But I was actually remarkably surprised by the creativity of the community. And there's like certain trends that have gradually surfaced over time. And I just want to pick a few of those just to give you an idea of the kind of content we're seeing. So first up, we're seeing macro splats. And this is essentially using macro photography techniques to generate the imagery that you pass into the Splat training software. And yeah, you can just get some incredible results from scanning very tiny things such as insects that you can see here. And if you head to SuperSplat, you'll see like most of the top rated splats are macro splats. Also, synthetic splats is something else we're seeing a wave of. This is where you're not taking photography as input to the splat training process. You're taking actual rendered images from applications like 3D Studio Max or Blender. And yeah, you can, with artificial input imagery, you can produce some pretty incredible results, much better than you could imagine with, say, a mesh-based solution. Next up, we've seen a lot of drone-based splats uploaded to the site. So this is actually a YouTube video that was just input into a splat trainer and then uploaded to SuperSplat. So as well as having like the original video, you've got a fully explorable 3D scene, which is quite a nice byproduct. We're also seeing a lot of multicam splats as more companies, it tends to be companies because it's quite expensive to build a multicam rig, but we're seeing more and more businesses set up these rigs and using them to capture target subjects, which otherwise would be rather hard to keep still. And some of the results are incredible. So this cat, for example, just a few megabytes, but absolutely not possible if you're going to do that with a mesh-based solution. Next up, LiDAR-based splats. We're seeing the rise of new devices such as XGrid's Portal Cam that really represent quite a step change in the fidelity of the output that's generated. You see an example here. Yeah, we're seeing a lot more of these types of splats uploaded to SuperSplat right now. Part of the problem with these kind of splats is that there's a lot of Gaussians in there. So quite early on, the PlayCanvas team was very active working on new compression techniques for Gaussian splats. The first solution we came up with was called compressed PLY. This is a quantized format. If you've also heard of SPZ, it's like they're very similar in how they're formulated. Yeah, they're based on quantization. And if we were to take this scene here, for example, which has a shade over 4 million Gaussians and 3 spherical harmonic bands, it's about a gigabyte. And if you quantize it down, you get it roughly 4 times. You get a 4 times reduction down to about 263 megabytes. Now that's not bad. It means you can suddenly run this thing on, say, a mobile device, but the end user is going to be waiting around for quite a long time for that data to download. So this was very much us dipping our toe in the water. After this, we moved on to a new technique that was built off the back of some incredible research done by Wieland Morgenstern on a new technique called SOGs. We call this SOG minus the S. And it's essentially the WebP of 3D Gaussian splatting, and literally the WebP of Gaussian splatting because it's based on WebP compression. And so this example here, you can see I'm just like cycling through the different the WebP images representing the splat. And what we're doing really is we're encoding the splat, the Gaussian attributes into a WebP image. And they compress remarkably well. So if we look at the results this time around, instead of 263 megabytes, we can crunch down to 58 megabytes. And that's a 17 times reduction of the original PLY. Now, this is much more like it because on a decent internet connection, we're talking about just a few seconds to time to interactive, which is great. So the whole SuperSplat website is now built on SOG and a lot of other software. You know, if you look at say splat trainers like Lifelike Studio, they have SOG integrated into them now, and it's been supported in a number of runtimes as well, in addition to PlayCanvas. Okay, so can we do any better? Sure we can. So if you take a SOG compressed splat and you break that up into a number of level of detailed chunks, it means that you can like stream a subset of the overall data set as you move around it. And yeah, so this splat is, instead of being 1 gigabyte, it's 8 gigabytes. And the initial payload to get the scene interactive is just 40 megabytes, even smaller than for the scene I showed you on the previous slide. So, and this is pretty much constant. So no matter how big your data set is, you're always just going to have to pay that initial 40 megabyte download size, and then the user can get going. So pretty cool. Okay, so I've got some exciting news, because today coincides with us getting this streamed LOD system into closed beta on SuperSplat. So here you can see the very first scene we uploaded earlier today, and I'm really excited to share it with you. This scene has 27 million Gaussians in it. Literally, while the first presentations were going on, we got a 208 million splat Gaussian scene running as well, but I didn't have time to record the video. But trust me, you can do hundreds of millions of Gaussians on SuperSplat now. So if you want to try it out, head to the PlayCanvas Discord, and we'd love to give you access. But very excited about that being released in the next few days. So how do we do this SOG compression? How does it work? We have an open source tool called Splat Transform. It is a CLI tool based on Node.js. So you just have to install Node, and you can install Splat Transform. And then it's just a matter of giving it an input PLY file, outputting a SOG file, and away it goes. Now, this tool is actually built on WebGPU, and we use Google's Dawn project to be able to run that in Node. And we need it to run on WebGPU because we leverage the GPU to do the compression of spherical harmonics, and we use a pretty compute-heavy k-means clustering algorithm to do that compression. But it works great, and if you want to use it in your own workflows while you're processing your data for runtime, then head to GitHub and grab Splat Transform. I talked at the beginning about the fact that we've spent some time educating industries on what's possible and enabling them to incorporate Gaussian splatting into their businesses. And I thought I'd just give you a few top picks. I did a little bit of an analysis of the various companies that are using PlayCanvas to do their Gaussian splatting, and it kind of broke down like this. So we're seeing about a third building platforms or tools to either edit, modify, share, publish Gaussian splats. Then we're seeing another 23% working in e-commerce, 15% in real estate or architectural visualization, another 15% in sort of cultural or heritage sector, and then lastly in sort of virtual production. Okay, so let's look at some concrete examples. First up, we've got CoStar that owns Matterport. So Matterport now have this feature called Matterport Exteriors that uses PlayCanvas to do the visualization of the externals of property listings, which I think is definitely like the future of like browsing properties online. And then we've got Nikon in Japan that have a facility to do virtual production, and they've created digital twins of their premises over in Japan, which are absolutely stunning. So check them out on Nikon's on their website. On the e-commerce side, we've seen quite a few platforms that allow brands, businesses to integrate sort of real-time splat-based visualizations of products on their product details pages. And what I want to highlight is Reflect. That's absolutely awesome from an UI UX standpoint. But yeah, there's several of these types of businesses that are springing up now. And we also have in the metaverse category Arrival Space that allow you to upload splat environments and then populate them with like either mesh-based objects or splat-based objects, create annotations, and also you can tie together these environments through portals and explore them socially with other users. But it's a really beautiful use case for Gaussian splats. And lastly, I want to touch on 4D Gaussian splats. So earlier this year, a company called 4DV went reasonably viral with 4DV file format that contains like a temporal format for Gaussian splats where you can like interpolate at any frame rate and you get like perfectly smooth animation. It's very, very impressive indeed, and they built this on the PlayCanvas renderer. So yeah, going into 2026, 4D Gaussian splatting is something that we certainly want to work on and build tools around. We can incorporate better support for that in the SuperSplat editor and also in publishing to the SuperSplat website. I just want to finish up by saying that PlayCanvas and everything that I've showed you today is free and open source. So I would encourage anybody to come and join our open source mission. If any of our code bases are of use to you and your projects or your businesses, then feel free to get started with them. Come and join the PlayCanvas Discord, and I'd love to help you get started. That's it from me. Thanks for listening. Any questions? I'm happy to answer them.
Amazing, great stuff, Will. And so happy to hear that PlayCanvas is getting even better with these new features. Personally, I'm definitely looking for this next year with what the integration of dynamic 3D Gaussians will bring to you. I'm so super excited to hear that that's on your roadmap, and we'll be happy to see that. Now, do we have any questions on the line? Okay, yes, first one from Jeff. On 4DGS, will SOG compression be used as well, or is there other active area in this work? I guess the question really is about the comparison to this 4DV format that you were referring to. So is that SOG based or is it something else?
No, it's not SOG based. We actually developed SOG after 4DV developed their format. And anyway, I don't believe that SOG would be a really good foundation for a runtime format. It might be useful for like an intermediate format that maybe could be like an interchange format or something. But for runtime, I think you need to support things that were mentioned in a previous talk, actually, where you need to identify, for example, parts of the scene that are static and parts of the scene that are dynamic, and just like do the interpolation for those Gaussians. And like SOG doesn't have that ability to kind of like store a time dimension per Gaussian or whatever. So I don't really see SOG being like evolved into a 4D format. I think it's more likely that we'll adopt something like 4DV. But this is something that we're really just sort of getting behind now. So yeah, anyone who's kind of working on the 4D side would be more than happy to work with you to get this all working in SuperSplat and on in the PlayCanvas engine.
All right, cool. So I guess we don't have any other questions. So it was a bit okay. One more. So where do you see the main use cases for 4DGS in the future?
Gosh, well, I mean, I think there's lots of interesting applications around digital memories, entertainment, education, travel. I mean, there's a ton of them, right? Like, so I'm really kind of excited to start exploring some of these things. But like I mentioned earlier on in my presentation, I went live with the SuperSplat website, and the people who actually creating the content never cease to surprise me with coming up with new applications. So, I mean, all I'd say is like, whatever I think might happen is going to be a tiny subset for what actually happens.
That's a great answer. I always frequently get these similar questions like, what are the use cases for this particular volumetric video? And I'm like, well, it could be anything. Like, was that the same question that they asked when they introduced 2D video? But yeah, sure. Okay. I think we can do with one more question. How about the capture devices? Do you always need a multi-camera rigs? I guess this refers to 4DGS then.
So if it's funny with the 4DV samples because they produced about 10 different 4DGS scenes. If you spin the camera around, you can see the edges of their multi-camera rig, and it looks like they've set up something like 100 cameras, roughly. So, you know, I think over time we will see a lot of research done into this that's going to like enable us to reduce the camera count. And, you know, like Gen AI will probably plug into this somehow. But yeah, for now, at least, you need a like relatively high number of cameras to get results as good as what I showed you in that video.
All right, brilliant, good. And one final question before we move on to the break. So does PlayCanvas engine aim to support multiple dynamic streamed 4DGS splats in the same scene?
Yeah, I don't see why not. I mean, one of the features I showed right at the beginning of my talk was this little engine demo. I mean, it's kind of subtle because it's not obvious when I show it, but we call it global sorting, where all of the splat content that we load into a single scene is kind of thrown into a work buffer, and then we sort the entire buffer. So like, there's no limit to the number of individual splats that you can play back in the same rendered scene.
All right, brilliant. Thanks for the quick answer. And with that, much appreciated. Thanks, Will, for spending the time with us here. And we'll move on to a well-deserved 8-minute break. So let's reconvene at 9 a.m. PT sharp. And we'll continue with Alex from Looking Glass. All right. I think it's time for us to end the break and get started with our new set of presentations. And as promised, we'll start with Alex from Looking Glass. So Alex, the floor is yours. Thanks.
Great. Thank you. Hi, everyone. Let me just share. Yeah, so my name is Alex Duncan. I'm VP of Software Product here at Looking Glass. We make holographic displays. And when we say holographic displays, we really mean displays where you can see 3D content as a group without needing any headset or peripherals or anything like that. We have worked on displays of many different technical categories over the years. We've worked with volumetric displays, light field displays for most of the last 6 years. And recently we have a new lineup of displays that we call hololuminescent displays, which I'll talk about at the end. I'll mostly talk about our light field displays for the purposes of this talk, though. Yeah, so we like holographic displays because you can walk up to them, you can see 3D content as a group. There's very little friction, and they're great for shared spaces. They're very different from VR displays, which we often get compared to, which is not a great comparison for us, actually. So if you think of VR displays as putting you into a virtual world that you're looking out at, you can think of our holographic displays almost as the inverse, where we're taking a chunk of digital 3D content and bringing it into your world. And it is a limited space. It's almost like a box of volume. And that makes it ideal for things like products, artifacts, people, characters, etc. It's not like a window into a digital world. But within that box, you have true 3D perception. So you have stereoscopy and you have parallax. And this is great for data visualization and things like molecular modeling, radiology, map viewing, etc. And we really focus in terms of industry fit on shared spaces. So places where you have high foot traffic. So things like museums, retail stores, educational spaces, and scientific visualization, especially in like reviews or conference rooms. How it works under the hood is basically, if you think of a regular 2D display as having a single view, a VR headset as having 2 views, one for each eye, that gives you stereoscopy. We emit up to 100 views in about a 50 to 60 degree view cone, and that allows multiple people to see the content at the same time. Each person is getting a different set of 2 perspectives, which gives them that stereoscopy. And as they move from side to side, they're getting a different set of 2 views, so they get parallax. We encode this kind of naively, actually. Let me just go back there. We basically have this format that we call a quilt, which we basically just take a standard MP4 or image file and we just paste the views into that image. And I'll talk a little bit about why we did this. And then what the display does on the optics side is that when we process that quilt and render it to the screen, it gives each of those views a direction. So it comes out of the display at a different angle. And that's how you get those multiple different perspectives coming out of the display without needing any headset to see them. We've had some success with this category of display. We've shipped over 20,000 systems to both consumers and to enterprise customers. And they've been deployed in lots of different spaces around the world. So universities, hospitals, pharmaceutical companies, amusement parks. I was actually just down in Orlando to check out an installation at Universal that uses one of our displays in a ride. So we are seeing adoption, which is great in a broad set of industries. And we've been able to build a pretty robust developer ecosystem and community. And I think, obviously I'm biased, but I think we are generally kind of considered a leader in headset-free 3D displays. There are other groups around there. We really focus on group viewability, so shared 3D perception. This is a screenshot from our Kickstarter campaign for the Looking Glass portrait, which helped really build that community. But we have also seen challenges, and I'll talk a lot about why this has been a hard thing to bring to market, holographic displays as a category. So a lot of companies buy our displays, but a lot of them buy like one or two. And they're in these processes of doing validation cycles where they're trying to understand the technology, where it fits into their business, how it can help push their business forward. And this can be a very slow process to get beyond that validation into large-scale adoption, because there is legitimate technical complexity in terms of how they create content, deploy content, etc. The technology is very horizontal, so we have adoption in many industries, and each of those industries has different sets of content, different requirements for deployment, different use cases, which makes it difficult for us to solve the problem end to end for a wide range of our customers. And I think that, you know, there are many things I'm sure we could be doing differently or better to speed up that adoption. But I do think with a more robust ecosystem around multi-view rendering and multi-view deployment, we could get acceleration in terms of the rate of adoption and the depth of adoption. We're a small startup. It's hard for us to push all of this stuff forward at the same time. So what is hard? A bunch of things are hard about holographic displays. So if we think of real-time rendering, which we do a lot of, so interactive applications, we have a lot of challenges with performance. So most engines, like Unity and Unreal, they're optimized for 2 views, sometimes 4 views, but we want 45 to 100. So we have to do a lot of customization of these engines to get them to render at all for our displays, first of all, but certainly to get them to render quickly. And this is obviously a challenge because now you're asking your customers to buy more expensive hardware to run these applications. And we have to do a lot of engineering work on our side to customize the tools so that they work at all. And even on low-level graphics APIs, there's not a lot of great optimization for really high view counts. So there are optimizations on like NVIDIA's APIs for up to 4 views, but doing more than that the tooling isn't incredible right now. So we have just like, it's slow to render this many views. This is kind of a funny one, but we have spent a shocking amount of time wrestling Windows, like window management on various OSs. So we often run, and in a lot of use cases, the customer wants our displays to run as a sidecar. So basically they have their standard setup. They plug in our holographic display via HDMI cable or whatever. And they want to have their 2D view where they're doing their regular workflow and their 3D view where they can see the content in 3D. This is really common in things like molecular modeling or materials science. We want them to do this as well. Managing that relationship between the OS and our display is actually more of a pain than I would have expected before being in this business. There are controls for this, like Microsoft's VSDB, but it's not cross-platform. And basically, what that lets us do in Windows is basically have the display say, "Okay, I'm a display, but don't treat me like a normal display. Like, don't pop up a window on my display. Don't show the regular background on this display because I'm a special category of display." This doesn't exist at all in Mac, which is a challenge. And Unity and Unreal don't really have great support for this out of the box, which again requires us to build more software. As a small team, this is always tricky. It's possible. There's nothing preventing us from doing this, but it is more work for us. And then we also have built a separate runtime that lets us hook into the window and manage it ourselves in a separate graphics context. But this requires developers, it causes some friction for development, right? Because now you have to understand this new system as a developer working in Unity or Unreal or whatever system you are. And now you have to hook into it. You have to understand how interaction works with this new graphics context. Kind of a headache. We aren't the first people to deal with this. This is a screenshot from an old Oculus setup where it's basically asking the user how they want the display to be handled by the OS. So some work was done thanks to VR headsets, which has been helpful, but it's still not a perfect ecosystem by any means. Offline rendering is maybe even worse than real-time rendering for our displays. You know, we get kind of categorized into XR because our display is 3D, but our displays are really truly displays first, and most displays in the types of places that I'm talking about, museums, retail, etc., they're actually not normally interactive most of the time. Most of the time they are showing videos. So rendering video content for our displays is actually really important. But offline renderers are really not optimized for multi-view rendering. So in these cases, it's usually just like there is no optimization at all. It's just take your regular rendering time and multiply it by 45, 100, however much, which, you know, you can imagine is a lot. We did a project with Pixar where they rendered out 2 minutes of video, something like that, for our displays. And we took up half a day of their entire rendering infrastructure at Pixar, which is a great story, but not great for achieving adoption because that is cost prohibitive for a lot of companies. Render farms and stuff aren't really set up to support multi-view rendering, so we have to do some customization there as well. And then in a lot of cases, companies that are showing video on a regular display, they don't actually have the 3D asset that was made for it, like the brands won't. So say a Chanel or a Nike, oftentimes they just have the end render that they got from an agency, which makes converting their content difficult. We can use things like, you know, depth estimation to get RGBD content, or there's now a new project called Segment Anything 3D, but these are new and they're imperfect. So getting videos onto the display is not easy, including from a storage and deployment standpoint. So, you know, for our 8K lineup of displays, for our larger displays, we want a quilt generally of 8K by 8K pixels, which is huge, obviously. And most infrastructure isn't built around it. There are modern standards like MIV, but these would also require us to do custom tooling. So media players like VLC and MPV don't support this natively. And probably more importantly, neither do digital signage players like BrightSign. BrightSign is a computer that's used in digital signage around the world. And they don't have built-in support for MIV. So we'd have to, again, customize more aspects of the ecosystem to create an end-to-end product. And yeah, these quilts require per device processing. So each of our displays has a unique calibration that is required to process the quilt. which means that we need kind of high performance client hardware because we have to take this big texture, decode it, process it through a shader, and then blit it to the screen. So again, we're asking our customers to adopt this technology, but there's additional cost and additional complexity at all these different stages. In terms of real world capture, this is something we've been talking about a lot or other folks have been talking about a lot, and I'm learning a lot about different options out there, but there's not a lot of out of the box light field camera rigs that are ready for businesses or consumers to adopt into their lives or workflows. And, you know, a lot of the processing, you know, in an ideal world, what we would have is just view in, view out. We don't need to do photogrammetry. If we just had a camera for each angle that we want to project out, we wouldn't have to process it at all. There are some really good algorithms like Gaussian Splats, like neural radiance fields. All this stuff is great. But again, it's new. It's not fully adopted across the industry. And we've done a lot of stuff with RGBD, like just depth maps, but of course that's not a full light field. We have to do infill, etc. All right, so with all these kind of complexities, we are still working on our light field displays, but we've launched a new line of displays called hololuminescent displays, or HLDs. And the reason we did this is we realized that there are two reasons people were adopting our technology. One was what we call like a 3D problem, where they have information, complicated 3D data sets, and they want to make it easier to understand, talk about, parse visually. So this is in like computational chemistry, mapping, etc. That's like a 3D comprehension problem, and that does require our light field displays, which again, we still sell, we still support. Other groups were really interested in our light field displays because they are interesting to look at. They grab people's attention. So we call this kind of the magic problem. And that doesn't actually really need a full light field. It needs something that's really cool, creates a sense of presence, etc. So we made this new type of display called a hololuminescent display that basically renders a 2D video and then has a physical light field embedded inside of it that creates this 3D alcove. And that lets our customers render and use just standard 2D video and makes this kind of immersive feeling experience for their use case, which helps with industry fit and adoption. And, you know, we're seeing adoption really in retail, food and beverage, hospitality, places where you want an interesting experience, but you don't necessarily need a full light field. And you can think of this as similar to like hologram fans or hologram boxes, but there are some advantages of this technology: smaller footprint, higher contrast screens. It films really well. So we think that there's good potential for this type of display. And moving forward, we are continuing to work on both our HLDs and our light field displays. But in the near term, we see the most immediate market fit in our HLD technology, especially in digital signage and immersive experiences. So this is our big product focus for the near term. We feel internally that light field displays need a little bit more time to mature, especially in terms of the ecosystem around them, before we can have the capability of pushing them forward in terms of adoption as a startup. But there is big opportunity here in pharmaceuticals, in medical, in mapping. We see industry pull, but it is hard to deliver on the expectations of all of those industries. But yeah, we're committed to this type of display, this category. And I think there is a big future for this type of display in terms of how people work with data, how they communicate, etc. So we're going to continue to work on this and hopefully collaborate with some of you all on this call to bring it to life. Thanks.
All right. Thank you, Alex. It was a welcome perspective into this capture and generation oriented volumetric video audience that we have today. So it was great to hear this brutally honest feedback from someone who's actually trying to bring this to the other side. So appreciate that feedback. And I hope that many of the people or participants in the call will make a dedicated note out of what was just discussed. So definitely there's still work to be done. in this
Well,
regard.
I mean, so many people on this call are doing really incredible work that we could also do a better job of adopting on our end, I'm sure. And it's been really interesting to see all the stuff that's going into this ecosystem. But yeah, definitely still challenges ahead to get widespread adoption.
Definitely. All right, so we don't have too many questions available, but I do have a couple of ones that, well, I mean, I had more of questions actually, but you kind of answered those by yourself just going through the presentation. So I was, yep. So question regarding this, the number of views that you put in this quilt. So is it really like a problem how many views you can put in this frame? Or is it a hardware or the display hardware side of problem? Sort of like, is there a limit how many views you can project from the display?
Yeah.
Or is it the decoder side of? Yeah. Okay.
It's definitely on both sides. So part of it is a limitation in the display panel pixel density. That is one limiting factor. We don't manufacture custom LCDs or OLED displays. We use existing hardware. And there's not a ton of use cases for super high resolution like 16K panels. They are actually starting to come out, but most stuff is capped at 8K right now, which as we scale to like our 65-inch display, which is our largest light field display, even 8K is less than we would like in terms of number of pixels to be projecting directionally. And then on the quilt side, that does cause that we can get more, we can get higher quality from the displays than an 8K by 8K texture that is a quilt gives us. And so we started moving away from quilts. We're using more texture arrays, etc., in our rendering stack nowadays to get higher per view resolution and more views. And we should probably be adopting things like MIV to push that even farther, but have not yet.
Okay, cool, interesting. And very interesting also that you bring up this MIV, which there was another presentation earlier from Chris on that note. So definitely maybe some common ground there.
Yeah, definitely.
Cool. All right. Well, thanks so much for your time and the presentation. I think it was absolutely needed for us. So thanks again, and we'll move on with the next one. So I see Michael already with the camera on and ready to get the presentation started. That's the spirit.
Yeah, definitely. No, thanks so much for having me here, and I'm really excited to be talking to everyone today about the emerging world of very lifelike, both static and dynamic 3D. And so to give just like a quick little background before I jump into my presentation, I run a website called radiancefields.com where I go through and catalog the progression of these radiance field-based technologies from like NeRFs to Gaussian Splatting to some of the voxel-based and ray trace-based approaches as well, all with the aim of really being able to centralize information surrounding the emerging world of lifelike 3D. So to jump in, when I was putting together this presentation, I wanted to pull this very recent quote from James Cameron that came out of a series of talks that he did at Meta's Connect just a couple months ago. And I think that he kind of very effectively showcases the potential use cases and where we will see very lifelike 3D pop up in our world. And for him and myself as well, he believes that we are going to interact with the world in a very natively 3D way, whether that is going through your sports, your social media, any like news or journalism. This will all be done in 3D because it's how we actually interact and experience the world around us. And so to also level set some of the technology that's been coming out recently, I want to start with grounding it in the initial 3D Gaussian splatting paper, which was published in 2023 from INRIA and was co-first authors Bernard Kerbel and George Kopanis. As a quick note, if you are a PhD student, Bernard Kerbel is actually looking for PhD students right now to advise, so I would highly recommend, if you are interested in working with him, that you take a look at that opportunity. 3D Gaussian Splatting won Best Paper at SIGGRAPH 2023 and has been very quickly adopted out into the real world. And since then, in just a couple of years to now, we've seen significant advancements, some of which Will highlighted from both the fidelity and compression and level of detail and tooling that PlayCanvas has also made available to the world. And to also ground things in the world of static, because I think it does directly feed back into the world of dynamic 3D, is there's a lot of adoption happening right now inside of the world's largest industries, as they're realizing that they can conduct their work in 3D with the same fidelity as normal 2D imagery or video. And so some of the industries that are really finding a lot of value with this technology include, architecture, engineering, and construction, and geospatial, whereby previously they were struggling a bit to be able to effectively reconstruct very thin structures or reflective objects or foliage or vegetation. This has now just been solved off the bat from Gaussian splatting, as being able to render at very large scale areas, up to the point where they are now rendering entire cities and have the capabilities to do much larger than even that as well. Another place where they're finding immense value in the world of Gaussian splatting has been both the autonomous vehicle and robotics industry, whereby they are now, I guess, you can take an entire city or a street and then simulate the actual synthetic car driving through it, and the cars are unable to tell that they are not in the physical world, and you're able to really be able to more effectively simulate some of these things. Other applications, I won't go through each one, but we see a lot of applications that are starting to merge in both defense and education, a lot in e-commerce. Will also highlighted both Zillow and CoStar Group, which are two of the largest real estate providers here in the United States, have now both activated support for exteriors with Gaussian splatting. And we're seeing really exciting ones too in the world of journalism as well, where I alluded to a little bit earlier. I think that this is a place where we're seeing the New York Times, we're seeing the New Yorker put out content using Gaussian splatting to more effectively demonstrate their stories. And it's my belief that we will see a influencing of all industries that currently are using 2D in some capacity. I think that we're now able to reconstruct and interact with the world in a very lifelike 3D way, and I think that these industries are going to or are in the process of realizing this. So we're here to mainly talk about the dynamic world, though, and just like static Gaussian splatting, the base input are just normal 2D images. And so we can see here's a collection of multi-view images of myself that was captured from the company Infinite Realities. I'm just going to let it play really quickly. And we can see there are all these various angles that are being captured across different lighting conditions, for instance, as well through here. And we can just see the amount of perspectives that are just being ingested into these systems. And from this, we are able to take those combined 2D images or video and reconstruct it into very lifelike dynamic 3D. So here is a little screen grab of Henry Pierce from Infinite Realities, and it looks just like nice little photographs, but we can see as well it's actually very nice video. And these very nice videos are actually not 2D videos, but these are actually fully dynamic 3D representations as well, which is just stunning, the amount of fidelity that we're actually able to now model and pull out of this too, as we can start to see the camera translate and move throughout the scene. We can zoom in and see the level of potential detail that Gaussian splatting allows us to also reconstruct. And so when we take a look at some of the progression of this technology, we've seen a lot of interest in the static world of being able to really create lifelike 3D. But in my opinion, we are now seeing a lot of attention move into the world of dynamic 3D representation. So we have static Gaussian splatting, which is akin to, say, photography and 2D images. And then we have dynamic Gaussian splatting, which is more akin to video. And we can see some of the places where Gaussian splatting, dynamic Gaussian splatting is actually beginning to be embraced within the world of popular culture and media and entertainment. And so here is actually an example that was a couple years already in the making and just released in, I think, July of 2025. And that is the most recent Superman movie, where if we go and take a look, every single shot of Superman's parents in this movie is dynamic Gaussian splatting, which was captured by Infinite Realities, and then the VFX work was done by Framestore. And what dynamic Gaussian splatting allowed this VFX team to do is it gave them a lot of creative freedom, whereby all of the upfront capture and work that they wanted to do was actually captured at the initial shoot, where they essentially were capturing all the angles, all the moments in time, and then they were able to then choose the focal length. They were able to reframe the shots as well. There was no additional reshooting necessary, but it gave them more time to actually go back in and decide, what's the best way to actually convey this scene's information to the audience, especially as the rest of the story progressed as well. And when I interviewed the Kevin Sears, the VFX supervisor from Framestore, one of the things that we spoke about was that the ability to actually create very lifelike dynamic 3D at a lower cost than traditional digidoubles or doing full CG reconstruction. And so they were able to dedicate a lot more time to actually other parts of the pipeline because they already were getting what they needed very quickly. And if you like as well, I do have that full interview link below at the bottom of the slide. So one of the exciting things is that we're seeing a lot of tailwinds emerging from these large tech companies as well. And some of these companies include both Apple. So Apple most recently has just confirmed that their personas, which is how people interact with the Vision Pro, are powered by Gaussian splatting. And so here's an example from a creator named Sadly It's Bradley, just kind of showcasing how lifelike and dynamic this representation is on the headset. One other really exciting tailwind as well is been the announcement of the iPhone 17 Pro now supports Genlock, and we've already seen companies like Radiant Images, for instance, and as well as Volucap as well in Germany, creating a lot of these rigs that are just lined with iPhone 17 Pros, and they're using it to work with dynamic Gaussian splatting. And on the other side, on Meta, for instance, we're seeing the continual advancement of their codec avatars program, which is kind of akin to Apple's personas, where we're also seeing super lifelike dynamic 3D reconstructions from a series of either 2D images or some other input. And I think it also really is being extended in some capacity by the recent success of Hyperscape Capture, which was also the newest form was announced in September as well at Meta's Connect, and that has had a very positive reception to it and has brought a lot more people into the world of just normal static Gaussian splatting, but starting to prepare the general population of saying, we now very much have the capability to bring the world into a very lifelike 3D world or representation. Couple other examples that are a little bit more recent. We've seen, Netflix's Eyeline Studios put out a lot of work and research in this same field. If you're going to be at SIGGRAPH Asia next month in Hong Kong, they're going to be presenting their most recent work, which is called DEGS. And we can see here the level of fidelity that we can get. And obviously this setup is very much so an enterprise grade setup where this is by no means an affordable way to do it, but we can see where we can be potentially thinking about this technology. And another really exciting vertical as well is coming out of NVIDIA's Amory Lab, which has put out works like Queen, which they've been doing demos at the various conferences such as GTC and SIGGRAPH this year. And so hopefully we'll see more work from these companies as a whole over the next year, but I think that it really helps signify the investment that's coming in from these large players into the world of very lifelike dynamic 3D. So with this same world, where can we take a look at dynamic 3D heading? And so we can see here's a quick little demo from the evercoast team that we shot together earlier this year, just of doing a quick monologue of some of the applications of dynamic Gaussian splatting. But I think that it's very likely that we are going to start to see the actual pop culture applications of dynamic Gaussian splatting hitting the internet. And some of the ways that I think that I would be not surprised at all for sure by the end of next year. I don't know if we'll see it by the end of this year, but I think that we will start to begin to see dynamic 3D Gaussian splatting concerts from various large artists as well, in addition to music videos too. Some of the productions that are out there right now are starting to really explore what they can do from a creative standpoint using dynamic 3D. And I think that we're going to actually see this a lot sooner than the general population might expect. And we can also then start to explore as well, how do we start to think about full feature films or larger or short films in some capacity too, where people, I believe, are going to start to think through, how do I start to effectively tell a story that is being shot in full dynamic 3D? I think that these conversations are also a lot further along than people might realize. And the final way that I think we could be seeing this is actually through YouTube and general social media content creation. I believe that there are a group of people who are looking at this as a full-on content creation medium. One of which I have actually linked below, which is a pair from the UK named Mike Karana and Brendan Singh, who have been actually going out on I would say kind of like a guerrilla Gaussian splatting setup and going out to actually just capture the world around them without, with essentially, I think they have something like 40 Sony cameras that they're going out and they're just shooting with it anyway. So it would not surprise me at all if we start to see content creators starting to go down this route, especially as people start to realize how lifelike this dynamic 3D representation can be. So I expect to see some of this content hit YouTube and other social media companies probably next year. And along these lines as well, what we're starting to see more so in the static world right now. So we mentioned on some of these last presentations with Will, say like the XGrid's portal cam, which I actually have right here. But this is a camera that is meant to shoot Gaussian splatting in static 3D. I would not be surprised to see essentially a spatial camcorder of sorts emerge over the next year as well that is more targeted to shoot dynamic 3D. So I think that we are going to see a pretty radical grouping of hardware-based designs over the next year to 2 years too. So some of these things are really exciting to actually start to think about, like how do we really start to capture and think about the world in natively 3D. One other really exciting direction too has been from the research world has been how do we start to cut down the amount of cameras that are necessary. We've seen a lot of this questions about what is the modularity of some of these camera rigs in the future going to look like. And we can see here is a paper called Diffie-Man from actually from the 4DV company that Will was referencing earlier on the call. And this is a collection of 4 cameras total, where we can see the sparse input on this here. And then when we go and actually add some diffusion models into it, we're able to recover significantly more information. And so I think that we're going to see a lot more research that starts to aim to actually aid from this reconstruction from a diffusion-based or general video model perspective. And I think one other part that Christian mentioned as part of his talk is that spherical harmonics has been kind of like there's a lot of thoughts as to what spherical harmonics might contribute towards the long future of Gaussian splatting. And it would not surprise me from another research direction if in the next few months we start to see alternate representations for these view-dependent effects that do not use spherical harmonics. So what could potentially help get us to a very lifelike dynamic 3D future? Here is a final version of that initial slide from the multi-view images of myself at Infinite Realities. And there are definitely still some hurdles to overcome here. And for me, I actually look at the world of dynamic Gaussian splatting and dynamic lifelike 3D as having a marketing problem right now, where I believe that the technology has far surpassed its capabilities towards the public's awareness. When we take a look at 4DV, for instance, earlier this year, who put out a couple of quick demos, we saw how quickly it was brought into the world of TikTok and YouTube and Instagram Reels, where there was definitely not a lot of information that was necessarily accurate, but there was a lot of excitement about the world of dynamic 3D. And I think that there needs to be more of an awareness that people can actually start to really recreate the world in lifelike dynamic 3D. And simultaneously, there's kind of like an additional challenge here is like, how do we effectively demonstrate that this content is not 2D? And this is something that I've been trying to think through a lot because it has kind of crossed that threshold of being indistinguishable from 2D. How do we actually let people understand that what they're looking at is no longer just like a flat image or slice? One other thing that I'd like to highlight is that I think having access to more accessible tooling, both on the capture side and the processing side, would be definitely still a remaining challenge, though I know that there's a lot of work being done in this regard. And the final thing is that I'm hopeful that as more examples of Lifelike Dynamic 3D hit the internet, that some of these social media platforms such as Instagram and YouTube and X or Twitter must support also having this as a content medium as well. So I'm hopeful that in the next few years, some of these larger providers and social media companies start to really take seriously some of these representations. So with this all in mind, we actually, myself and Infinite Realities have open sourced this data set where it is a little bit over 300,000 images of me and also contains 1,800 trained PLYs, in addition to also having the ColMap data in a pinhole format as well with the undistorted images. So if you would like to request access to that, there is the link as well for you. And so just wanted to quickly highlight some of the capture studios that are around both North America and Europe. So if you're curious of like, where can I actually go to see some of these examples, here's just a small collection of some of them that I have listed in alphabetical order. There's a lot of really cool examples here, one of which is a company called Myris as well, which is also looking into the live streaming capabilities of dynamic Gaussian splatting as well, which is taking a very cool approach. And all of these links can actually be found on my website, which is just radiancefields.com/platforms. I've tried to make it a bit filterable for people to explore and find information. And just another quick little thought here. Yeah, the world of radiance fields, so like Gaussian splatting, is just moving incredibly quickly. And so I've been working hard for coming up on 3 years on the website and 4 years total in the space to try and actually centralize all this information to make it more digestible and keep track to the actual progress of this technology, because I think it's just going to get quite a bit more exponential from here than in the past. I've definitely seen this over the last like 6 to 8 months, I would say. And so hopefully if you're looking to stay on top of the information in this field, please consider checking out my website. Or if you're looking for consulting services, please also feel free to reach out as well. And yeah, thank you. And happy to answer any questions that you guys might have.
Brilliant. Thanks, Michael. Amazing. Such an energetic presentation as always. It's a pleasure to view this. It's not my first time being in the audience for your presentation. So yeah. Questions. I think there's one from Jeff. So how do you look at the utility of 4DGS versus generative video models for real world use cases? Will companies still care about capturing real performance if they can generate whole cloth?
Yeah, I think it's a very interesting and open-ended question right now, where I'm not sure the answer to this definitively. There's been a lot of work from companies like, say, like World Labs, and I know there's a lot of companies that are also looking at just single like monocular to full dynamic Gaussian splatting pipelines as well. I'm not sure how it will actually proliferate yet, but my hope is that at the end use case we will still have access to very lifelike dynamic or static 3D content from it.
Mm-hmm. Cool. Then to your question, you were actually asking us how would you really convey that the medium is 3D rather than 2D? So definitely one way to look at it would be from Looking Glass. There's a ball to be thrown on Alex's court there. Could be really nice like that. And of course, you get all of the head-mounted displays to some point. Like if you consume 4D Gaussian splats on a head-mounted display, that's where they really come to life, and some amazing experiences there. Yeah.
If there's a couple companies like Gracia, for instance, has quite a few dynamic Gaussian splatting examples that you can look at on a Quest 3 or 3S that I would really recommend to anyone who's listening. That you can see like the full like view-dependent effects still in dynamic 3D, and it's very exciting.
Yeah, exactly. Like the specular effects on the salmon. It's brilliant. Okay. One last question. I'm donating a bit of my time from the next slot. It's going to be really hard to follow this presentation, so thanks for that. Last year, we were talking a lot about sports-related use cases. You were making bets that music could be maybe the next one up. how do you feel about sports-related use cases in general for 3D Gaussian splats? Like, does it follow a similar timeline? Yeah.
Yeah. I think that there's a lot of really exciting work being done. In the sports arena, there was just a really cool SIGGRAPH paper called things like Echoes of the Colosseum, which starts to deal with some of these questions. The sports one, I think having it close to real time is still like a ways off for like Gaussian splatting. But I definitely have seen some of these thoughts be revised as the pace of research accelerates. So I think for right now, it's still very much like in the world of research, but we'll see.
All right, cool. So with that and no other questions on the line, so let's move to the next slot. I'm going to spend the next 15 minutes roughly reviewing the state of volumetric media. And this is about this survey that we conduct in MSF annually, where we set out a questionnaire to the industry, trying to figure out where we are headed as a whole, and try to somehow derive our position in a hype cycle, if you will. So yeah, here are the findings from this year. Okay, so first up, the general intention of the survey is just to figure out who's working in this industry and what kind of momentum we currently have. This year, we got 25 responses after sending the questionnaire to some standard setting organizations in the domain, and generally to places where we expect volumetric media enthusiasts to be found. So kind of the results here reveal a bit about the biases also about the survey. So these are from the experts of the industry. They're not necessarily always very outward focusing. This year, though, we received a bit more responses from organizations that are not directly adjacent to volumetric media. And we could see that this is a sort of a positive trend that volumetric media is kind of trying to preach out to outside of its core domain, if you will. Regarding the company profiles that were answering the survey or replying the survey, so this also reveals a bit about where the industry is headed. So a large portion is still working on technology for technology providers, meaning companies that are pursuing developing the ingredients for volumetric related experiences rather than the kind of customer facing side of the organizations. This is down quite a lot from last year, but still by far the largest share of the responses. Another thing worth pointing out is this hiring profiles for companies that are actually hiring. So last year, by far the most sought out terms or positions were for software developers. But this year that has gone down by 20 percentage units. So that's quite a big share or shift in the type of talent that the companies are currently looking for. And where we see the increase then is that companies are looking actually more to get business developers and content production specialists. So those two categories have seen quite a big increase. A general note on the kind of amount of open positions and how the trend, how the volumetric media related organizations have grown over the past 2 years is that it has largely remained the same, or somewhat increased. So last year, we got 46% of the responses saying that they have actually increased their size of their volumetric media related resources. And this year it's about 30%, so a little bit down. But at the same time, the size of these organizations have then largely been the same as it has been for over the past 2 years. So there's not as much growth necessarily in terms of headcount as if you look at it that way. But the interesting thing and the important thing is that there's not a reduction either. So people were either declining to disclose the information or So yeah, this all seems to suggest that the industry momentum around volumetric media is indeed increasing, but slightly less rapid pace than a year ago. And this might be interesting or somewhat contradictory to some of the presentations that we just heard, where we've seen the 3D Gaussians and 4D Gaussians kick off tremendously. Like it's closer to the mainstream adoption, I would say, than last year, but the momentum somehow, at least in light of these numbers, is somewhat decreasing. Now, when it comes to volumetric media consumption habits, some things to note is that the weekly number of volumetric media users have actually significantly increased. Last year, only 17% of the respondents consumed volumetric media on a weekly basis. This year, it's about 44%. Significant portion is still not consuming volumetric content still not consuming volumetric content, or it's only consuming it on a monthly basis. Last year, it was about 62%. This year, it's about 35%. So quick, great progress, but this is still a very large share of the overall respondents. In terms of the new device categories people are using to consume volumetric content, I think the autostereoscopic displays is worth a shout out here. It's seen an increase from 8% to 24%. Otherwise, the phone and tablet form factors, laptops, desktops, and head-mounted displays have largely held their dominance on experiencing this type of content. In terms of the use cases, we were trying to map or understand where volumetric media is useful. So generally, the applications that would be most suitable for volumetric media versus what use cases are actually driving the market adoption and where organizations are currently focusing their efforts. There's no significant major findings here. I think what needs to be emphasized is that the sports, entertainment, and music related use cases are generally very dominant here. They are the ones that are seen as the seen as the best use cases, seen as the ones that are actually driving more adoption, and then of course companies are also working on them. But then if we look at the key market drivers outside of this segment, we see that education, communication, and gaming are the type of use cases that companies expect to be market drivers. But then on the other hand, where companies are really focusing is education, business verticals, and art, which is slightly different from what we believe would be driving then the market adoption. I think this is partly due because companies will obviously need to figure out where the money is currently. They can't just focus on building the market. They need to also fund their short-term ventures, and focusing on specific business verticals makes a lot more sense from that perspective. Future outlook. This is an interesting question that we keep on tracking year to year. So when do the people expect mainstream adoption to take place? And by mainstream adoption, we refer to adopting volumetric media in non-specialist use cases and into everyday usage. The big difference this year compared to last year is that last year, majority of the responses were falling in this 3 to 5 years time span. So 49% of the respondents believe that within 3 to 5 years, we will see mainstream adoption of volumetric media. This year, it's only 37%. Now, this difference or delta has split into two categories, either going nearer term, so 0 to 2 years, or flipping to 6 to 10 year bucket. Now, the average or the median is still well within this 3 to 5 year timeline. But I just found it a little bit interesting that it's been either moving closer to adoption or further from adoption. And just a bit peculiar. Now, we had also a question where people would be putting the volumetric media as a whole on a hype cycle. And these responses, as always, are quite distributed. The general trend is that seem to be moving up towards the peaks and plateaus So we see fewer responses in the technology trigger and throw of disillusionment domains, whereas we see slight increase in the slope of enlightenment and at the peak of inflated expectations. So definitely we have a trend upwards. Whether we are going towards the peak of inflated expectations or towards the productivity remains to be seen. There's hard to draw conclusions based on this single data point, but yeah, definitely an upwards trend here. Now, in terms of the future outlook, in 2024, we asked if about 2 billion euros or dollars would sound about the right size of the volumetric media market as a whole. This was largely agreed by the respondents. They saw it fairly around the right ballpark. Whereas this year, we used another study that evaluated the size of volumetric media markets around 7.19 billion. And this actually got a little bit of pushback from the respondents who felt that this number should be somewhat or even somewhat more lower. So yeah, take it as you will, but it's still kind of good indicator of what the size of the volumetric market might be. Now, the second part of the question was related to this compound annual growth rates. In 2024, the evaluation was 28% compound annual growth rate, which is really high. And now in this new study that we were using 2025, the expectation was 15.42% compound annual growth rate. And this is somewhat agreeable by the respondents. So they do believe that this 15% CAGR is pretty good prediction going forward. So putting these numbers into perspective, of course, if we look at Netflix and their 2024 revenues, it was 39 billion, so 7 billion or whatever is left of that. It's a lot less than Netflix. So the market is still like in the early phase. And then if we look at the CAGR, so the growth potential for reference, Netflix 5-year CAGR predicted forwards is about 10%. So 15 is still way above the sort of the market average, I would say. Now, we also asked the question of how to speed up the adoption of volumetric media, and we got some nice, interesting results here. Now, I think the delta of the responses gives a bit more insights than just the the graph of this year alone. So if we point out the enabling better form factors and devices for consuming the content, it got 67%. This 67% in importance this year, whereas last year it was only 37%. So it's a 13 percentage unit jump from the year before. So definitely, this is something that we should look into in the future of how to make volumetric media somewhat more consumable to the users. The device form factors and the device form factors obviously will play a significant role here. Another thing to mention here is this enabling more affordable experiences. So this is again something that resonated with several of the respondents. So this is something that 54% of the respondents believed was going to be critical this year, and it was only evaluated 33% last year. So a very significant jump there. And the takeaway is that we should be definitely looking into these two things, better form factors and more affordable experiences going forward to help the markets adopt this technology. Now, the significant change to the other direction is on the evaluation of developing higher quality experiences. So this year it got 50%. Last year it was 79%. So this is a significant reduction. Something happened during this year that made the respondents feel that, hey, maybe the quality might be getting there. Maybe we no longer need to look for massive jumps in this domain. Maybe we need to look into other areas for improving the markets. And another point that saw a significant reduction was this making more content available. So last year we had 75% evaluating this as the most critical action or activity for the industry. This year, it's only 36%, which means that something must have happened. More content have become available. I don't think we can take credit of us highlighting this point last year that we need to produce more content for people to use. But again, some really interesting large shifts in this perspectives, how to speed up the adoption. And lastly, we had a kind of an open-ended question or asking what should the industry focus on as a whole to enable a healthy ecosystem. This year, the answers pretty much highlight the importance of standards. So these are, by the way, in the order of preference or priority. The number of similar points raised during the feedback. So first one is about standards. So that was the most important people felt. And they were just listing various different types of standards related to capture, to data formats, to compression and content playback. And at the same time, they were highlighting that, okay, the standard should be only deployed for the right problem. So maybe these four are the sort of right problems or not, remains to be seen. Another point was emphasizing the importance of improving usability and affordability of tooling for capture, generation, distribution, and consumption of volumetric media. And this is something that I've heard being highlighted a couple of times already today. So people really were making the point on this, making better tooling. And thirdly, better technology marketing towards end users, B2B, and content creators. And I think this one at least resonated partially with what Michael was just saying, that maybe the technology is already there beyond what the markets are expecting. We're just not doing a proper job of communicating that. And then as a summary, I think we're gradually moving towards more widespread adoption, slightly smaller share of technology vendors in the responses, more focus on business development and content production, and less focus on software development. Significant increase in the number of people that are consuming content weekly. So this is great. However, while we're going forward, it seems that the industry momentum is somewhat decreasing. The pace is slower than a year ago. As an example, the sizes of volumetric media organizations are only slightly increasing, not growing as much as they were growing a year ago. The estimated size of the volumetric media markets has increased significantly, but at the same time, the CAGR for the next 5 years have somewhat been toned down. In kind of a conclusion, we might be still looking at like a 3 to 5 year adoption span for volumetric media in the mainstream. What we should do definitely as an industry is we should put more emphasis on creating better form factors, more affordable experiences, and more unified experiences. So more unified experiences means kind of the standards need to be there in place. People have fewer concerns about creating high quality experiences and making content available. I think that's due to Gaussian Splats and radiance fields and the advancements that we've all witnessed during the past year. And we need to keep providing better tooling, and that should be a high priority for everyone. All right, good. And with that, I think we're 1 minute above the schedule. So maybe one question if there are any. I don't think there is any. Okay, good. Well, in that case, let me switch. Oh, actually, let me not switch. We will get started with the panel. And I will just need to introduce the panelists once I refind the sharing button. There we go. So, all right, good. We have the panelists online. And Andrew, could you please turn off your video? All right, brilliant, thanks. So good. Introduction of the panelists. We have Denny Breitenfield from Skyrim AI. He's a new technology veteran with over 20 years of field experience. At the start of 2022, he founded Skyrim AI to focus bringing real-time broadcast quality volumetric video to the sports media industry. And also Denny is the president of VFA, but he's here today with his Skyrim AI hat on. So welcome, Denny. Then in addition, we have Ben, who we already heard from during the speaker slots from EverCoast. He is a co-founder and CEO. He's held numerous C-level titles in multimedia companies such as Little Star, Birdbox, SIF, and most recently, as I said, EverCoast. At EverCoast, he focuses on building a volumetric video platform for virtual production, mobile XR, and the metaverse. So welcome, Ben. Then we have Will Driscoll, a co-founder of Fitsu. He's an LA-based spatial technology entrepreneur, inventor, and creative technologist, currently focusing on fashion fit intelligence at Fitsu. He used to work as a CEO of and co-founder of Wild Capture, which many of us probably know. And he has contributed to several high-profile productions, such as Megalopolis and Wild West from Intel Reality Studios or something like that. So welcome, Will. Glad to have you here. Next up, we have Alex, who we also heard of during his presentation on volumetric displays. He works as a VP of software product at Looking Glass and manages a team of software engineers and product designers at Looking Glass, which is a Brooklyn-based startup that makes these holographic displays. He's currently focusing on building the plugins, applications, and web interfaces to create the content for the devices. So welcome, Alex, and appreciate your time. Next up, we have Marius Breda. I think most of us know him from being a convener at MPEC on the 3D graphics and haptics working group, but he's also an associate professor at the Institute of Mines in Telecom. And he leads a research team with a focus of XR games and interactive media. Extremely active contributor to several journals and speaking engagements worldwide. Welcome, Marius. Nice to have you here. And last up, but definitely not least, we have Devin Horseman, who is the CTO and founder of Arcturus Studios. He provides the technical and product vision for research and guidance to build software that saves countless hours in the production of volumetric video. And as a peculiarity, Arcturus was definitely among the first wave of early 3DGS adopters last year. In 2023, when in November already they announced their support for 3D Gaussian Splats. So glad to have you here, Devin. All right, I will take the question panel somewhere where I can actually see it so that I can scroll the questions as they come up. So a hint for everyone online, please submit your questions using the Zoom chat if you have something that you want to submit. And yeah, let me stop sharing so that we get the speakers here. All right, brilliant. Okay, now I lost the Zoom. No, it's the Zoom chat again. Okay, here I got it. All right, so let me then, in the interest of saving, not waiting for questions to appear, let me get started with some questions of my own. So let's start maybe with a softball. And this is directed to everyone, all of the panel members. So what are the ideal device form factors and use cases for consuming volumetric media? And let's start with Ben.
Well, I'm just going to say that certainly the Looking Glass, 33% of the panelists here are located within approximately 2 miles of each other, and that is EverCoast and the Looking Glass team. So Alex is just up the block from us, but yeah, I mean, certainly non-headset driven devices are important. So the goggles that we have today are limiting and isolating for a lot of different sort of mainstream applications. So we see most of our sort of content land on two-dimensional screens on just TV broadcasts or iPads or mobile devices. These are the devices that exist in mass, and using volumetric as as data to display on those devices is fantastic methods. And then some of our data never even sees the light of day in terms of it like sort of actually being visualized. In some cases, it is just numbers that are going into a model. And so, there are certain use cases where volumetric data is not necessarily being visualized, which opens up some interesting use cases and opportunities.
Okay, great answer. And I sense the ball must go to Alex after this one.
Well, yeah. I mean, I am a strong believer in Gaussian splats, and even some of the ray-based rendering techniques for Gaussians. I'm really interested in. It was really interesting to see Gaussian splats kind of come up in the industry and continue to come up, because to me they really are the content side of light fields. Like, it is the other side of the coin when it comes to light field representation, Gaussians and autostereoscopic displays or light field displays. So I'm obviously a strong believer in our displays and other autostereoscopic displays being great endpoints for this type of content. As I talked a lot about in my presentation, we have to meet the customer where they are today as well, as much as we try to build for the future and want to build for the future. So we don't just render Gaussians on our displays, but yeah, an excellent like technology fit, certainly, even if the industry adoption maybe is still coming up.
All right, cool. Devin, maybe you next.
Hey, yeah. So I think the content question is perhaps the most interesting one at the moment. And if we're talking about where the market is today and how things can be consumed today, we have to kind of consider what the value chain is, going from the capture of the content right through to the end user. And if we think about that, when we think about the expense of producing this content and the desire to not have each capture be a one-off, then things like sports media and other live events at regular concert venues ends up being one of the most interesting use cases. The reason there is you get kind of repeat use with a single setup. You get the space to wire and put all the right equipment in, and you've also got a ton of value being generated from this content. So for an NFL game, you might have viewership of 5 to 8 million, maybe even 15 million in some cases, and that generates a lot of advertising revenue. And that advertising revenue can cover the cost of the capture. And if the captured content, does more to drive, viewers behavior, then that's a winning equation. So that's one of the reasons that we're seeing things like live events and sports kind of bubble up to the top of use cases right now. It obviously introduces a ton of challenges on the capture side, on the distribution side, and that's a bunch of the insights I'd be happy to share today from our learnings.
Brilliant, thanks. Then, Danny, your insights on the device form factors and use cases?
Obviously, looking glass, of course, but the other area that we're focusing on is a smart TV. So that whatever you're watching, whether it's an animation in 3D or sports, that there's a way for the active viewer to be active, and there's a default way for the passive viewer to just enjoy the game and let them sort of move between the modes whenever they sort of get inspired by what's going on in the content. So smart TVs is our North Star.
Amazing. Will?
Hi, everybody, and thanks, Laurie, for everything. This is my first entering this conversation. A lot of I agree with Ben with the 2D display being kind of where most of it occurs. We with wild capture, we were sort of on the post side of things. So a lot of it was cost savings with scheduling. So now with Gaussian splatting, you can have two actors in separate locations, an environment in a third location, and tie the whole scene together. That's going to be a huge benefit in where 2D goes. The other side of it is cross-media campaigns where you've got talent only for a few hours and you need to generate the core content as well as token assets, print media, web interactive sort of stuff. So, trying to get the bang for the buck has always been sort of the answer because cost has been the biggest barrier of entry. I've seen a lot of interest in experiential theme parks where there's ride queues and you need to keep people entertained, or there's an event space and they want to increase foot traffic. So they're starting to do more advertising, product sort of marketing, sort of brand stuff.
Cool.
Thanks.
And Marius, your few cents.
Yeah. I think that we should answer from at least two perspectives, in the sense that what is ideal in terms of technology and what is ideal in terms of current deployment. And unfortunately, today, the answer is not the same. We know that ideal with respect to the technology would be the hand-worn devices or whatever, AR glasses, VR, and so on. But if we are staying there, volumetric content will be a niche. So the proper answer, at least today, is that the ideal device should be what people have, massively have, in the sense smartphones, tablets, and probably also large devices. So I think the way, at least for a time, before inventing the ideal device that will benefit fully from the immersiveness of the experience, should be smartphones and tablets, and not because they are ideal, but because they are massively deployed. And somehow we have to make our technology work nicely on that device and producing comfortable experience for even on a flat device. And having that because someone mentioned before, I think was Michael, how we realize that the content is 3D on a flat screen. If you give the possibility to interact with and to change the perspective, the camera position with the finger, that is a simple answer. Of course, it's not ideal, but I think for a while we have to also go in that direction.
I think you make an excellent point there. Anyone care to build on that?
Yeah, I just wanted to jump in and say that I actually, maybe contrary to expectations, I couldn't agree more with that. And actually getting more adoption for volumetric content on 2D devices will help our business, because then we have more people in the ecosystem that are already working with this content that will work even better on a light field display. That's actually great for us. So I think, as much as I would love for everybody here to be building volumetric content just for looking glass displays, that's not the reality of where we are with the technology. And building and getting adoption in 2D devices will help us a lot.
All right, brilliant. Why don't we get one question from the audience first? On the topic of non-rendered use cases, is there any sense of how much opportunity exists for creating datasets for example, humanoid robotics training? Last year, one of the use cases that we were talking was training AI with the volumetric video.
I mean, I think
Ben, you mentioned that.
Yeah, it's a substantial part of kind of what we're doing, and the idea that this type of data can be leveraged to train any sort of AI, whether it's a physical AI that's powering a robot or a digital AI that's understanding physical therapy, medical application. There's a lot of ways in which this data is getting used to train generative models, completely generative models. You probably saw, even some of the reduction in camera counts, being able to go from large camera arrays down to smaller, sparser arrays. Those are all kind of a lot of that's rooted in some of the machine learning that can leverage a lot of this data to get there. So we've seen. So to answer that question, I think in terms of how much opportunity exists, I think it's hard to sort of it's a bigger conversation around market size and such, but I think there's certainly good opportunity there.
Cool. Anyone else?
Yeah, I can just mention that we've seen an increased demand across our company for generating data sets. Perhaps not as much as we might have expected, but I think we expected a fairly significant amount. So yeah, there's definitely market demand. I don't know if it's something you could build a full startup on right now, but it's there.
Yeah, I've seen the demand for it, but it's like a roadmap demand with FitView. The company I'm building currently, we're doing fit intelligence, which essentially is virtual try-on focused on purely fit. Style is an addition to it, but what we're doing is range of motion, musculature changes from pose. That's how it sort of plays into measurements. And so down the road, the 4D dynamic, as we were calling it, Michael's calling it, could play a factor for analyzing, measuring people in motion.
All right, down the line, sounds like something you might want to look into after the call.
Yep.
Cool. There's another question on what is currently the lowest latency pipeline from volumetric capture to rendering. For example, on Unreal.
We have one that goes, it's in about
Ben. Yeah.
300 milliseconds is about as fast as we can go from camera lens to rendering inside of Unreal Engine over a network. So that's actually transmitting over public internet. So it's about as fast as we can go. And that's cool. full 4D, full 3D scene.
Right. Obviously, a lot of this question also boils down to the quality that you're expecting. You might be able to distribute some quality at a very rapid pace.
Yeah, I mean, we're not doing our Gaussian splatting pipeline is not 300 milliseconds.
Sure.
Right now.
Yeah, I think talking about what's the best balances of quality versus compression, I think you can get in the roughly 40 megabit per second range in roughly under 5 seconds with a sort of patch-based codecs that they're reasonably good quality, reasonably performant rendering, and reasonably small data rates. I think if you're looking for the lowest latency solution today, that is, sort of where we might all call acceptable and fairly robust. That seems to be the I guess kind of the best balance of factors that we've seen. If you want to go lower data rates, there's mesh-based live codecs that can deliver in about 30 seconds. I've seen other codecs that are sort of sub 10 seconds, but I don't know their data rates. So couldn't comment on that. When you're getting up to 3D Gaussian based solutions, I think the best rates I've seen for those are around 30 seconds to a minute, and those are with quite controlled circumstances. I would expect that right now, a typical solution there would sort of kind of be roughly 15 to 30 minutes that you'd see data turning around. Yeah, those are the comments I have, but just based on my experiences of seeing a bunch of different technologies.
Yep.
For what we're doing, we can do 900 milliseconds with up to 256 cameras at 1080. Excuse me. When we do 4K at 256 cameras, we're at 1.2 seconds, glass to glass. And if we go to 8K, we're at 2.1 seconds end-to-end glass to glass, up to 256 cameras.
Yep.
And that's with
Probably
the
also depends on the-
patch-based solution, Denny? Yeah, okay.
Yep. Also probably depends on the use case. So Michael briefly mentioned these Apple personas and Meta's codec avatars, which can give you real-time communication scenario at extreme high quality, exploiting Gaussians to some extent. Any thoughts about these type of hybrid representations? They're obviously coming. Any relation to volumetric media as such? Let's maybe take who wants to go first?
I can speak to it.
All right, cool.
That's actually what got me into Gaussians, was to be able to manipulate them. What we're doing with volumetric video, the mesh-based forms, was with Wild Capture, we created something called the Unify Solver, which created coherency start to finish of a mesh sequence. And so what that gave us is a deformer lattice to be able to manipulate the point clouds. So we shot a music video actually with Ben and Evercoast for a known rapper where he's known for over-the-top stuff. So we had to do a lot of visual effects. There's a team of animators who are traditionally, character animators. We're able to manipulate the character and whatnot. And so it was taking still frames of the performance with pose estimation married to it and sort of tying it together for a full robust pipeline. And it's very similar to what the both of those technologies are using.
Right. Devin.
Yeah, I think an important aspect of talking about codec avatars is what purpose they're meant to solve for the end user. And if the answer is what's a plausible view of what's going on right now, then they're a really great solution. Obviously, they're not very flexible. If you pick up props or you change your outfit, or even if you're, blushing or, something of this sort, you're not necessarily going to see all of these things appear in the avatar. So if we're talking about plausible but not, real, then they're a pretty good solution, and there's a lot of cases where they'll be useful. But if what matters is what actually happened, then they add quite a bit of confusion to the situation, and it can even be used, to sort of hide the truth. So, what is it? What does it look like when, for example, the risk of having somebody pretending to be someone they're not, or the ability to even just to hide your emotional, how emotions come to your face, or something of this sort. So yeah, there's risks. There's certainly benefits.
Yeah, absolutely.
I think I have a different take on it, Laurie. You look at this coming December in America, there's going to be 2 NFL games that are going to be sort of an alt cast. One of them is Nickelodeon. They've been doing it on CBS for, I think this is the 4th season or 3rd season, and they're blending 2D content with 2D CG content with 2D games. But imagine where it's actually volumetric players captured, but you're adding SpongeBob or you're adding Mickey Mouse, and maybe they're going to catch the ball or they're going to do the end zone dance. And you see that with the Monsters Inc. ESPN simulcast. And I think there's a world where the younger generation that isn't maybe into sports, this is a way to get them in with content that is more relevant, and then transition to the volumetric stuff.
All right, cool. I think we can move on to the next question. So there's an interesting perspective offered by Thomas. So what they observe for larger scale and consumer products is the need for static 3D content that you can interact with. Dynamic seems to not be relevant or at most in a very short sequences. Wondering if we should focus on 3D GS before we jump to 4D GS. Any perspective on this?
Yeah, for sure. Yeah, because it's easier. It's not because it's not relevant, but it's just because it's easier. Easier to capture, easier to represent, easier to send to the user and render. But it's like Obama said, because we can, of course. But people wants to have dynamic. Of course, a lot of people are using images, and it's fine. A lot of people are using videos, 2D videos, and it's fine. Our world is 3D. So step by step, we are going towards where we are. We are 3D people in a 3D world and dynamic. But indeed, I agree with Thomas. Yes, that the first step would be the easiest one. Let's do it for static content. Create a lot of content, put it on databases. People will look at that, install applications, and then they will say, "Oh, dynamic is better." And then we are preparing for dynamic. This is a good first step, but not enough.
Yeah, good. Anyone else care to build on that? No? Okay, cool. Yeah, definitely agree. Let's start with the images and work our way towards video. Like both have their place in the world for sure. Let's maybe take a question then. So this volumetric survey that I referred to, we were seeing a shift from making more content available and improving the quality to enabling better form factors and and devices for consuming the content. What do you believe are the steps that we as an industry should do to lower the barriers of adoption for mainstream? And why don't we start with Alex this time?
The adoption to mainstream for what exactly? For the
like
content?
lowering the barriers for adoption for the mainstream.
I mean, I think it really starts. Well, I guess it starts with use cases, but from there it comes to the cost of content production. Like this is something that has prevented us from getting more adoption in many like clear instances where we had a big project that we were working with a customer or a potential customer to bring to life. And when they looked at the cost of content production for volumetric, it was like significantly higher than the cost of our display technology, any of the software that we provided to render or run the content, the display hardware, etc. So I do think that there is a content bottleneck right now in terms of the cost of producing it. Obviously, tons of people are working on this and doing incredible work on this, but I do think that is legitimately a bottleneck at this point. Yeah, on our side, in terms of getting more displays out in the world, I think that would also help to have the flip side of it, like demand coming from autostereoscopic displays for this type of content could also help the ecosystem. But it's kind of that classic chicken and egg problem where if there isn't enough content, it's hard to justify the cost of a light field display. If there aren't enough light field displays, then what is the demand for volumetric content? I think volumetric content has far broader applications than just our displays. But certainly there's a back and forth there.
Yeah. And maybe Devin, I think we heard briefly on your perspectives on this particular topic already, but if there's anything you want to still fill in.
Yeah, I think there's a couple of things here. So we did have an issue with reaching what would be comparable to broadcast 2D quality previously. I think we're there now. The ability to get broadcast quality volumetric content is now here. So that's sort of a check. We've got that one in the bag. As far as live scenarios where we think most of the value is, if we sort of think about, generative content eventually coming and overtaking most use cases for creating stories that are sort of made up or more fantastical or more narrative driven, then a lot of the value will sort of reside in things that really happened, not things that are plausible to have happened. And for those scenarios, getting lower and lower latency is of a lot of value. So there's that sort of trade-off between latency and quality. And I don't think we have something that's both got the latency and the quality that the market demands. And then the third is the proof of value to the people who are paying for this work. We need to demonstrate that viewers, consumers are preferring this content over other content. We need to show that it drives an increase in revenue for people that are using it. And we need to find an honest way of measuring that, which takes quite a bit of risk from all the parties involved in creating those experiments. So I think that those are, if I would cover the three, first one solved, second one feels like we're on the way, but not quite there yet. Third, it's a lot of people have to hold hands and jump. And I think we're on the cusp of that. So I'm feeling pretty good about where things are headed.
Great, and incredible insights there. Anyone else care to chip in?
I think I'm going to put on the VFA hat here. I think standards are going to help drive the adoption. I think I agree with Devin. I think the quality is there. There's a here in the U.S. there's a documentary on PBS about the American Revolution, and they're selling a DVD. And if you think about a DVD, it's SD. And so I think the content and the quality meets that minimum, and that's a viable product that's being sold this holiday season. And DVDs will be in every big box store. So I think the key differentiator here is the standards. I think if the standards exist, then the content will be created with the quality we have today. And back to DVDs, you look at the height of DVDs, 40% of some of the major 6 studios, their revenue is from DVDs. So that's the peak that we're talking about. Yet there were 1 million people creating DVDs outside of the big 6 because of the standards. And I think if we can move towards that, I think we'll have an explosion of content.
Great. I think you're on the right track there. Standards were definitely mentioned that one of the biggest things to work on as an industry. I'm also, so to address these points that Devin was making, what other type of activities we should engage on to kind of accelerate the adoption? Why don't we go to maybe Marius then? I mean, the standards is an obvious bridge to your direction.
Yeah, I may add my point on the standards. Of course, that I agree completely with Danny, and I think many people here. But I would add that there is something in the existence of the standard that is implicit, but not fully captured by everybody. Is not because a standard is good or not that is important. Is because it is a standard, because it stabilizes. We are in a moving map, a moving target. Everything is in motion, and having some points in different parts of the chain, of the pipeline, that will stabilize the ecosystem, and people can build on top of that. So there is always a fight: which standard is good, which standard is less good, and evaluation. But that is not the point. The point is to have standards, and the best standard is not the one that will do PSNR of whatever. The best standard is the one that is easy to implement, easy to understand, and everybody can take it with no friction. So I think in MPEG we have this in mind somehow, and we are also creating standards with this purpose to be easy to use. However, in volumetric media, all of them are very complex, but not because we try to make them complex, it's because volumetric media is complex. We are speaking here about different form of representation, going from multi-view, video, point clouds, meshes, Gaussian splats, is a mess by itself, even before talking about compression. And then when you put on top of that compression, you will have yet another requirement, yet another solution. So it's a mess. Having a standard is very important, and having easy to deploy standards is even more important. So that is because I'm a standard guy. But I think that we also have some other places where we have frictions, and the one I see relatively big is on the capture side, because now to have volumetric media, we have to have a kind of multi-view camera installation. And that can work very well in professional studios. That can work very well for some sport events, but I hardly see it at home. You know, people at home, even if they have 10 phones, because every home today have 10 phones. Maybe we should create something to put all the phones together to have this capturing system at home. I don't know if that is the solution, but I'm more thinking to a kind of mixed solution when you have already a kind of acquisition of your 3D body or 3D object, doesn't matter, with probably several cameras, and you can do that in a studio. I have my own representation, a 3D representation, and then only using one camera while I'm in real time to change that representation into what I am at that particular moment, which would be a kind of hybrid volumetric capture plus one or two cameras for real-time part. That is not an easy architecture either, but somehow we have to invent things that will get out of this capturing friction, because I think our real problem is there.
It's an excellent point. And definitely on these standards, when you're working on something that's in active research, it's kind of difficult to create a standard that would be then very concise and coherent and not trying to leverage all of that research that is constantly brewing. So it's a difficult sort of equation to work with. There was a question earlier on whether or not evercoast is planning to make some content or some part of their system open source, and I think Ben sort of left a little teaser to that question. So I'm wondering if you had any perspectives on what other types of approaches might help us to accelerate volumetric media to the mainstream.
Yeah, I mean, so I think a lot of us on this call have had to build, you know, an end-to-end capability, and just because it didn't exist. And so, you know, when we started diving in, many of us into this, you know, many years ago, there was nothing to just go, you know, pull off the shelf and go do. So we had to build it. You know, what parts of that are, you know, critical to, as the ecosystem has evolved from, you know, from capture all the way through to, you know, playback and consumption on devices. You know, what pieces of this, of what we all might be building become specialized and become, you know, done better by others or by an open source community. You know, we didn't have Gaussian splatting, you know, just, you know, before 2023, and we're all building our own, you know, our own pipelines because again, in many ways we had to, and now sort of, you know, the open source community or sort of, you know, people put out Gaussian splatting and you know, a lot of people have adopted that. And so from our perspective, you know, do we want to be building some sort of, you know, codec and, you know, playback containers and things like that, while also trying to focus as close to the, you know, camera and hit on what Marius was talking about and sort of making capture, you know, easy, and then everything in between. It's just a lot for any one company if you're not, some huge massive company. If you're a startup, where do you end up focusing your resources? And you can do that and in certain verticals and just sort of go after one vertical and try to own it end to end, or you can sort of stay horizontal and break up your perhaps break up some of your components into things that you focus on and perhaps open source others. So we've built certain things at the client side, on the the codec side and container side and playback that we think that if perhaps if we open source some of that, maybe that'll just sort of help the community. I mean, we've got SOG, we've got other things that are open, but perhaps the more there is, the more people can just jump into it. And we've particularly focused on 4D components there. So that's kind of how I see just sort of the ecosystem and what we might evaluate putting out there as completely open.
Cool, excellent. I think we've been kind of frequently being referring to these captures as a problem, and how to bring that even to the consumer space, to prosumers and others. How do we get them to adopt these type of capture systems in their homes? How do we make the capturing part easier? I wonder, Will, if you had any thoughts on this.
Sure. Yeah, it's sort of tying a little bit of what Ben's talking about, that pretty much everybody's talking about now. We're sort of in a salad here, but back to the avatars where you can template an avatar in a higher end studio and then drive it at home. I agree that's probably where we're headed, because then you're really only having to manipulate blend shapes of the face essentially, and then you can tie I'll spare the deep dive right now, but we can assume we can sort of see that play out much easier than one or two cameras generating the back view with no information of any kind is clearly, we've seen a little bit of that with that Holograms group did that years ago, but it's for quality. You tend to need that good data in to get something good out, and so I see that being sort of the direction. But what's exciting about the Gaussian splatting is that technology opened agnostic hardware. So now you can use cinema cameras, which is also making high-end production more excited about this. When you say, hey, you can film this with the red camera, eyes perk up now. And the hair details there, the face details there, this and that. Whereas now, even on the indie side of it, there's the open source solutions if you want to do something small. But what I liked about working with Ben and Evercoast on I want to call it low budget, high results. The production management of the system was the other part of this, is being able to see the dailies, being able to piece that together is going to be part of it, where if you're a storyteller, you need all those pieces. You need to be able to tell the story. And up until this point, there's just been like one technical explanation for this or this. At capture, hey, if you shot it this way, you get this result at the end. Oh man, I wish I shot it that way. Or, in post, how do I track this object onto this person's hand? You need tool sets. And so as we as a community come together a little bit more on that, the high end, the mid range, the prosumers, the indie people will find this, adopt the open source solutions, and hopefully graduate to professionals.
Cool. Anyone else care to chip in? We could also build on this. Oh, Danny, I see your mic.
Yeah, I agree with the entire panel, and even what Maurice was saying. We've been talking about this with lots of folks, and I think either it comes from the media entertainment industry, or let's use the another industry, say the baby monitoring industry, right? Whoever sort of can provide value at a commercial success, and then if that contributes back to standards, that's the holy grail. It doesn't matter what the standard is about where you place the cameras here versus there. It's somebody has demonstrated it as value, like a baby monitoring system. You can see your baby in 3D, make sure they're okay breathing, or sports, whatever breakthrough it is, and it's commercially successful. And if that contributes back to any standards organization, then that'll lead to adoption.
All right, cool. Anyone else have any thoughts? If not, then I'm kind of curious on this. So what Will referred to was sort of like creating yourself like an avatar representation with a full scan somewhere else. Do we always need these high quality capture studios for getting high quality dynamic or static 3D GS data? Is it something that can generalize well to the prosumers and others? Ben, maybe you have some thoughts.
I think it's akin to just about any sort of form of video production today. We have Hollywood film, budgets, and we have, each of us with a phone in our hands and a lot in between. And, much of this comes down to just the professional, expectations of what does quote unquote high quality mean as output. What are your lighting conditions? What, lenses are you shooting with? And this is putting generative aside, I think which we should never do, because, the generative components of this fusing with real world data, will become, a material, thing and application here. But nonetheless, I just think that there's going to be this spectrum of what needs to be shot inside of, a studio, and what can be shot, completely out in the wild in situ in a factory or out on farmland. So there's just a wide range of kind of what high quality means. And then again, to the extent that you can use generative techniques to sort of use sparser arrays, make that easier, the better off we're all going to be, everyone's going to be. And then there's just sort of the complete, someone mentioned World Labs earlier, and as that becomes dynamic, to what extent are people able to completely hallucinate or use highly limited prompts with text and a single image or video or something, and create a completely dynamic 4D world. And I think somebody else kind of asked about that, and about does that render camera-based sort of capture useless? I don't think so at all. I think there are so many cases where like the authenticity of what's being captured matters is completely paramount. We've talked a lot about sports, and some people are super focused on sports. It is one of those use cases where like, you're not going to hallucinate what happened at the, in the Super Bowl, right? That's not what people want to see. In a lot of ways, people don't want to see their favorite celebrity being some generative character. There's no, real life Instagram feed. They're not going to see them on the red carpet. They're not going to follow their train wreck divorce. None of that stuff's going to be like real. So they just, it can't just be all generative. So I think there's just super important components of our life and as humans where, real world capture truly matters, and you have to get more of the real world into these, whether it's a simulator or onto your television screen. It's just fundamentally important.
Yeah, I would definitely agree. Anyone else to build on that?
I would say exactly the same thing in the sense. So the answer to your question is no, we will not need always that high-end studio, because what we don't have in hardware, we may have in software. So there are a lot of image processing techniques where you can improve the quality even if you don't have high-end cameras. And then together with this generative neural approach where a lot of things will be compensated. And I think that even we will have more and more content that will be generated, not computer generated, but generated, and that looks very real, and a lot of people will look at that content. So indeed, I think that we will go in the right direction. And if we look what happens from point cloud meshes and Gaussian Splat is exactly that. We are compensating the precision of the geometry reconstruction with some impostors. Gaussian splats are impostors. If you are old enough, you remember the 80s when we used impostors in 3D graphics because we didn't have the budget to have triangles. And now we are coming back. Of course, we are better impostors because they recreate the visualization, but in terms of geometry precision, a Gaussian splat is not at all precise. So I think we are going in that direction, compensating the lack of precision in capturing with advanced visualization, advanced or less advanced, but new visualization techniques.
All right. I think we're coming close to the end of the meeting, so I really wanted to get a couple of more insights from you. But can we take sort of quick fire rounds? So let's talk about what type of considerations need to be made regarding different types of venues when it comes to the quality of volumetric video. So stadium scale, home studio, well-lit studio somewhere else. Any thoughts on this particular question? What are the key considerations that you need to keep in your mind when you're setting up your volumetric capture systems in these scenarios? Devin?
Yeah, so we're mainly concerned with in-venue captures. We've also done a ton of studio capture in the past, roughly a decade of it. But you know, lighting is something that's important for the environment. Let's just talk a little bit about like the way cameras need to calibrate and how the quality of those images will impact how we solve. So with newer solvers like 3DGS, there's quite a bit of impact from not having images that have the same exposure, the same white balance, et cetera, et cetera. That stuff can be compensated for in the solver, but it's going to cost you time and processing performance. And latency for these sort of live events and venues is a really important aspect of the value being created. So anything you can do to limit that, the impact of that, like on what we call online calibration, where we're calibrating at the same time as solving, it's good to limit that as much as you can. So for example, doing a solve first, calibrating, and then using that calibration throughout the rest of the capture. For some things, you may not be able to do that. For example, the camera poses, you could have cameras that get bumped if they're on truss and that truss wiggles. You need to calibrate per frame online as you're solving, that kind of thing. So there's a lot of thought that goes into how your cameras are placed, how your cameras are calibrated, both calibrated for the specific lenses and the specific sensors in each camera. How you mount the cameras, how those cameras deal with being shaken, all these sorts of things all start to enter when you bring this stuff into the real world. So those are a few of the points of view. Once you get past the cameras, then you have to start thinking about, okay, how am I going to wire this? How many cameras can I fit on one line? If I've got to put 50 of these in this stadium, how many lines am I going to need? What technology am I going to use to transmit the signal? How am I going to move that signal over the existing networks of the venue and all this sort of thing? So a lot of know-how involved with that, and a lot of creativity you can bring to bear and organizing and building out those systems. So all really interesting stuff, and it is sort of where the volumetric video technology world really runs into the existing professional video world. There's a lot of learnings and know-how from that world too that can be applied to our cases, and we could always do a better job of learning and using those existing standards too. So yeah, it's a couple of thoughts.
That's plenty of thoughts. Thanks for the detailed explanation. Not really the quick fire round that I was looking for, though. So maybe I'll try one more question with a very simple answer, hopefully. So this is going to be the last question, and this is going to be directed to all of you. When do you believe volumetric media will enter mainstream markets? I'm looking for an integer response. Ben, let's start with you.
3 years. I don't know. I think it's such a. I don't know. It's a really tricky
fluffy
question.
question.
Loaded question. What does
Yes,
mainstream
indeed.
mean? What is it? Yeah, what does that really mean? But I think it's, to a point where everybody has, is consuming it actually in 3D. We're very dependent upon, devices or some sort of second screen experience on an iPad, and so until that is, maybe that becomes mainstream, where you kind of have these second screen, experiences or something. But I think for all of us to be kind of walking, around in volumetric land is still a ways away.
3 is good. Definitely overflooding the integer buffer with the rest of the response. Denny?
12 months.
Oh, nice. Alex?
For the display side, I think we're 3 years out. Maybe
Okay.
the content side sooner on other types of display.
Great. Devin?
Next year.
Okay. Will?
I'd say 2 to 3 years. I agree on that, like 2.5D, if you will, if you get what I'm saying, like that sort of almost there, not quite, but robots projecting Princess Leia on the ground, probably 7 to 10 years. So, that's what we really want. Let's all, the holodeck and actual holograms. So if we're being honest, 7 to 10 years.
Fair enough. All right, Marius.
Yeah, I would say if the question is for industry and investors, I would say, guys, put your money now, because this volumetric media trend is not only for seeing one person in 3D and moving around. That would bring a huge wave of new technology. I don't know yet how it will be used. We have something in mind, we have some use cases, but what I know for sure is that because we are doing this, we will create huge new markets.
Yeah, definitely agree. I think I can't remember who made the same point earlier on. So regarding, we don't know yet where this will be adopted. But
we've seen
we've
seen mainstream stuff today. Like, there'll be something coming out next month that's mainstream. It's gonna be It'll be massive. It'll be very widely viewed, that all leverages volumetric. But I think we just need to define, like, what does mainstream really mean to all of us.
Okay. Yeah. With that, then, Skip had a hard stop, and we've overused our budget. Skip, do you still have couple of minutes to spare, or are we done?
Unfortunately, I have a call waiting on the other line. I got my 10-minute recap ready to go. Maybe I can do a extra video that you can add on.
Yeah, let's do that maybe later. Sorry for going over time.
Okay.
My bad. So with that, then, we've filled the quota in terms of minutes, and sorry for going a bit over time and missing the wrap up. Amazing set of presenters, speakers, and the panelists. Really insightful thoughts. So thank you so much for joining us this year, and I hope to see many of you next year as well. And good stuff. Let's hope that next year when we're here, we have the mainstream adoption done. We can tick that box. Brilliant. All right. Thanks, everyone, and enjoy the rest of the day.
Thank you.
Bye for now.
Thank you, Laura, for pulling it together. Appreciate it.